Hi, good afternoon, everyone, and welcome to S3A, Singapore Symposium on Sentiment Analysis. This is an event that we have once every 2 years, and we started back in 2013, so this is the fifth edition. And usually it's really just a physical face-to-face meeting that we have with institutions and researchers from Singapore. And so usually the attendance is about 50 people. This year, for obvious reasons, we decided to go virtual, and we had a lot of participants. In fact, a lot of people have registered. In fact, I'm hoping that we don't go beyond 300 participants because sadly my Zoom subscription can only cover up to 300, but I see only 68 people online so far, so we are doing good for now. Okay, so this year the event is kindly sponsored by Graphene, which is an AI company that is revolutionizing market research. If you are interested, you can search, you can check out this website. Their website is graphenesbc.com. Also, if you're interested in joining them, in fact, one of my students has joined them and is very happy about it. Maybe later, if there's time, he can share his experience. So the format this year is very light. Every speaker is just giving a sort of elevator pitch in just 10 minutes. Each speaker, we have speakers from NUS, SMU, SUTD, A-Star, and even Alibaba. They're sharing their latest investigations in the context of affective computing and sentiment analysis. And so roughly we'll have like 10 minutes for each speaker plus 5 minutes for question answering. So as usual, we have an international invited speaker, Fabrizio Sebastiani. Fabrizio, are you there? Uh-oh, he's not. So the reason why we are doing this at 2:30 is because otherwise
here.
it would have been a bit too early
Can
for
you hear me?
Fabrizio. So
Can you
I
hear
hope
me?
he didn't fall asleep.
Can you hear me?
Oh, yes, yes, I can hear you. Sorry.
Can okay. My mic was muted. That's
Yeah,
fine.
no problem. So Fabrizio really needs no introduction. He's one of the guru and pioneer of sentiment analysis, and is associated with the Italian National Research Council, which is the top research institution in Italy. And today he's gonna share with us his recent investigations about cross-lingual sentiments quantification. And this is a paper that has just been recently published in this relatively new department of IEEE Intelligent Systems that I invite you to check out. So without further ado, if you're ready, Fabrizio, maybe you can share your screen.
Yes, let me try to share my screen. Um, can you
Great.
see my screen now?
Yes, yes, we can.
Okay, that's good. Okay, so thank you very much, Eric, for inviting me. And the talk I'm giving today is about sort of what I would call a novel task, cross-lingual sentiment quantification. It's a task, just let me check because I can't, okay. Um, so it is a task that departs from traditional sentiment classification, binary sentiment classification, because we are going to cover binary today only, in two main ways. Okay, so one is cross-linguality. So we abandon monolingual sentiment classification and we go cross-lingual. And as many of us know, cross-lingual classification is the task that is important when we have no training data for the language or languages for which we want to issue predictions that we here call the target languages, but we have instead training data for the same set of classes for a set of
Hello, I cannot hear you.
Yes, Fabrizio, we lost you. Suddenly you became muted somehow, but you're not unmuted. Okay, maybe he's restarting his Zoom. Unfortunately, this is one of the shortcomings of going virtual. In fact, in the beginning, I wanted to ask every speaker to send me a pre-recorded video as some conferences do, but then I wanted really to keep this interactive, and so I decided to go for the live option, but maybe it wasn't such a great idea. I hope Fabrizio is coming back soon. Let's give him another 1 minute. If not, maybe we can go on with next speaker and then we can come back to Fabrizio later.
Hello, good morning. Sorry for the delay. Nice to meet you.
Hello.
Hello.
So for those who just connected, we started the symposium already, and Fabrizio, the international speaker, was giving his speech, but suddenly something went wrong and he disappeared. So we're waiting for a few more seconds, hoping that he will get back online. If not, we'll just go on with the next speaker. I hope he's online already because he's supposed to speak at 3 actually.
Yes, we talk. I'm online. So
yeah, great. Good to hear.
Time you ask me to go, I will. Yeah, I will just wait. Yeah. Okay.
Let's wait another few seconds because Fabrizio actually has woken up so early for us, and I think he has some technical problems. No, I don't see him coming back. So in the interest of the workshop, I would proceed. So then maybe he can speak after Hwee. Okay, Hwee, do you have? Are you a co-host already? Are you able to share your screen?
Sure. Let me do that. Yeah, just a second. Just give me a minute. Okay. It says host disabled participant screen sharing.
Really?
Yeah. Can you enable me to screen share?
We don't see your screen.
No. I tried to do screen share, but I got an error message that says host disabled participant screen sharing.
That's so.
Erik, probably you have to authorize him.
Authorize? How do I do that?
I just made you a co-host.
Okay.
Try again.
Sorry, what?
Can you try again now?
Okay, sure. Okay, good. Yeah, looks okay now. Yeah.
Okay.
Can you see my screen?
So many technical problems. Yes, we can.
Can you see my screen? Okay, great.
Yes, please go ahead.
So can you hear me, everyone?
Yes.
Okay, good. Let me go ahead and start. Okay. Right. Good afternoon, everyone. So this talk, the title of this talk is Feature Adaptation of a Pre-trained Language Model Across Domains and Languages for Sentiment Classification. So this work is jointly done with my PhD students, colleagues at Alibaba and Soochow University. So this work has been published in the EMLP conference last year. So in sentiment classification, the input is natural language text. And we want to determine the sentiment class of the input text. What sort of a sentiment is it conveying? Is it positive, negative, or neutral? The challenge here is, how do we build a sentiment classifier that can generalize across different domains and languages? Because the reviews that we're getting can be about different products, different product categories, and written in different languages. And not all of them are present in our training data. So the standard approach to do this is to carry out supervised training for each individual domain and language. So in this approach, we need annotated text in each domain and language. And this is label intensive and hard to scale up. So our goal in this work is to build a sentiment classifier without annotated text in new domains and languages. So more specifically, as an example, our training data could consist of reviews written about the books, domains, written in English. But during test time, we are given reviews on another domain, perhaps electronic products, written in a different language, for example, Japanese. In our work, the only resources that we need are labeled review articles in the source domain and source language. That is, for the target domain and target language, we do not require review articles that are labeled. Since about 2 years ago, the kind of baseline way of building an NLP application, including sentiment classifier, is to leverage a pre-trained language model, such as BERT, its various improved variants like Roberta, BART, as well as multilingual pre-trained language models such as XLMR, and so on. Now, by leveraging the pre-trained language model, we then adapt its parameters on a new task such as sentiment classification, and based on adapting, fine-tune the parameters on this data set and this new task. This approach is largely effective, but it is sensitive to different distributions across domains, and its effectiveness is much weakened when we want to test on documents from different domains. So we need to adapt a pre-trained language model to different domains. So in this work, we propose unsupervised domain adaptation, or UDA, with the features from a pre-trained language model. In particular, we use self-training to predict the labels on unlabeled target domain data. We perform feature distillation using noise contrastive estimation and predicted class information. This is a model architecture. So we leverage a pre-trained language model, in particular XLMR. This is a cross-lingual language model published in ACR last year. In a cross-lingual language model, the words in different languages are mapped to the same vector space, such that words with similar meaning in two different languages are mapped to nearby locations in the vector space. In this way, we are able to bridge the language divide because all the language tokens have been mapped to the same representation vector space. We also have a feature adaptation module, which I will describe in detail soon, as well as finally a linear classifier, which just output the predicate probabilities across the sentiment classes. Our pre-trained language model XLMR is the transformer-based neural network. So each layer of the transformer has a hidden vector for each token. So we average the hidden vectors in layer L to form H bar of L. Then we build a feed-forward neural network with attention mechanism to compute a distilled vector Z. Now, the weights in our pre-trained language model are frozen during domain adaptation in our work. To carry out domain adaptation, we use a loss function comprising 3 components. The first component is LS, which is the standard cross-entropy loss based on the distilled vector Z, relying on the label data from the source domain. The second component is the cross-entropy loss, but now based on the automatically predicted pseudo-labels on the target domain. And the last component is the loss function correspond to our class-aware feature distillation, or CFD. So I explain LT and LCFD in detail now. So LT constitutes the self-trained component. So here we have our model predicts automatically the labels on the target domain data. Because these labels can contain noise, so we select a subset of the target domain data with high quality labels. These are the instances for which the labels can be predicted most confidently. In other words, they are the ones with low entropy. So these instances in the target domain are ranked higher. In addition, we want to diversify the instances across the different classes so that each sentiment class has the same number of predicted instances. I now go to the last component, this CFD loss of our domain adaptation approach. Recall that each layer of our transformer pre-trained language model generate a average vector HL. These average vectors sum up to form this X bar vector. Now, we want to maximize the mutual information between the distilled vector Z and this X bar vector, since both vectors come from the same document instance. So we want to maximize the mutual information between Z and X bar, but it turns out that directly maximizing the mutual information is difficult, and therefore, instead we maximize the lower bound of this mutual information metric using noise contrastive estimation, or NCE. So we want to maximize the similarity using cosine similarity between Z and X bar, because, like I say, they come from the same document. In addition, we randomly sample X negative number of randomly chosen negative samples in such a way that, we want this randomly sample negative example to have low similarity with our Z vector, because they come from different documents. So this noise contrastive estimation is a form of contrastive learning, and our goal here is to maximize this mutual information between Z and X bar. The last piece of our CFD loss is to minimize the distances between instances belonging to the same class, so that the class of instances within each class are more cohesive and they're clustered closer to one another. Specifically, for each class, we compute the centroid vector ZC, and then we compute the distance between each instance and this clustered centroid belonging to the same class, summing over all the instances as well as all the clusters, forming this quantity LC. So to summarize, our last piece, the third component, LCFD, comprises, first of all, maximizing the mutual information, which correspond to minimize the negative of this quantity here, as well as minimizing this LC, which is the distance of instances within a particular class. So now describe the evaluation of our approach. So we test on 2 data sets. First is we call mono Amazon, comprising Amazon reviews, but these are English-only reviews. They come from 4 domains, about 4 different product categories, namely books, electronics, beauty, products, and music. The second data set we call multi-Amazon. These are also Amazon reviews, but in addition to coming from 3 different domains, they are also written in different languages, namely English, German, French, and Japanese. For comparison, in our evaluation, we compare our system, which is UDA for unsupervised domain adaptation, against several state-of-the-art methods, namely MMD, KL, and adversarial, based on various metrics to minimize the losses across domains. In addition, we also compare a full-blown domain adaptation method, which is UDA, against components, again, variants of systems where successive loss function components are removed. UDA minus CFD corresponding to removing the loss CFD function, loss function component. UDA minus CFD minus ST correspond to removing LT and LCFD. That is, this UDA minus CFD minus ST is just training on the source domain without performing domain adaptation. And this is the classification accuracy on the monolingual Amazon datasets where we evaluate cross-domain performance. So you see that our full-blown method UDA, the blue color on the leftmost column, leftmost bar, outperforms the previous state-of-the-art methods on domain adaptation on sentiment classification, which is the 3 green bars on the rightmost side. In addition, UDA, the full-blown version, outperforms reduced versions of our component where the third, as well as the third and second components of the loss functions are removed. So this shows that each of our components, the self-training and the class-aware feature adaptation module with NC loss are contributing to performance improvement. The same results are obtained when we evaluate on a multi-Amazon datasets, which is on cross-domain and cross-language scenarios. So finally, in conclusion, we propose an unsupervised domain adaptation method for sentiment classification across different domains and languages. We employ feature adaptation of pre-trained language model using class-aware feature distillation with noise contrastive estimation. And our proposed method outperforms prior state-of-the-art methods. All right, that's all I have. Thank you. I'm ready to take questions now.
Thanks very much. Very nice. It's quite impressive that you can do multilingual and different domain at the same time.
Thank you. Yeah. Right.
Any questions from the audience?
Guido, can you show page 14?
Page 14. Okay. Let me
Yes.
do my share screen again. Okay. Page 14. Just a second. Yeah, here.
Yes.
Okay. Yes.
Can you briefly explain this equation?
Sure. So this is our third component, right, which we call the LCFD. It in turn consists of 2 subcomponents, right? First of all, this is the lower bound of the contrastive noise contrastive estimation loss, and the second part is to minimize the distances between examples within the class.
Thank you.
All right. Okay. Any other questions?
So do you need to do any segmentation for languages like Japanese or Chinese?
Okay, we don't do any word segmentation, right? So, you know, what happened is in the XLMR, the cross-lingual, the pre-trained cross-lingual language model, it actually has been split into sub-tokens. So just based on whatever the splitting, right, that's done in this pre-trained language model XLMR. And I do not think they do any word segmentation.
Mm-hmm.
In fact, they want to split to below, you know, below the token level so that it can promote generality, right? So you can overcome different morphology, right, of morphological rich languages. Right.
And do they handle in any way word sense disambiguation?
Well, in an indirect way, yes. I mean, you see, all of this contextualized language model, right, including the XLMR that we do, right? They do this transformer self-attention layer. So through this process, I mean, you get contextualized vector representation, which takes into account the context of the word, so that the same word will get different vector representations depending on the context of surrounding words. So in that sense, it sort of have this, sense disambiguation built in implicitly in what it's doing.
Right.
Right. Okay. Yeah. All right.
I can see a question in the chat. Not sure you want to take it. Someone is asking,
okay. What is the? Let me see. How do I get to the chat? Let me see.
I can read it for you. I can read it.
Okay. Sure. Yeah. Can you read it? Yeah.
They're asking if this can be used for aspect-based sentiment analysis.
Okay. In aspect-based sentiment analysis, I mean, you have to identify what is a more fine-grained task, right? Where you identify so-called aspects, right? So you don't just say, well, is it positive or negative of the whole document, but rather on the aspects, the particular words, features or properties, right, of the document. So I believe so. I mean, this is a very generic framework, right? That can be applied to classification tasks. So you need to first carry out the extraction, right? The extraction of the aspects, and then you classify each extracted aspects into positive or negative sentiments. So I mean, all of these preaching language models have been applied to also kind of token level kind of tasks, where for each token you predict whether is it aspect or not an aspect. And then if it's an aspect, what is the sentiment clause? So I believe you can do similar kind of things, right? Really as a classification task and do aspect sentiment classification, sentiment analysis.
It's a good idea for some future work.
Yep. Yeah. Okay. Right.
Okay. They're thanking you for answering the question, and I also thank you for your talk. It was really nice, and lucky you were online already. So thank you very much.
Thank you. Yeah, I will sign up. Yeah, I will. That's all for me. Thank you very much, everyone. Yeah, bye.
No problem.
Yeah.
Okay, I see that Fabrizio is back. Fabrizio, are you there? We can't hear you, but I see you.
You can't
Yes,
hear me?
I can hear you now.
So was there a problem with my presentation? I was presenting now.
Yeah, at some point after slide 2 or 3, you just disappear from the meeting.
Oh my God. I was presenting slide 19 and I hadn't realized that you were not.
Now we can hear you.
I don't know what happened.
But just now we cannot hear you. Suddenly you disappear.
So do you mind to give us your talk again?
Sure, I don't mind, but the problem is that we are late. No, it's not a problem for me. It's not a problem for me. I don't know whether it's a problem for you, but
no, it's not.
am really
sorry. Just went on with the next speaker who just finished. So you can go ahead now. We're perfectly in time.
Okay, I really apologize, but I didn't, I didn't hear anything from you.
Yeah, I'm sorry.
Probably audio had.
No, you just you really disappear from the Zoom meeting. I don't know what happened.
So I disappeared from the Zoom meeting.
Yeah, you were not.
I was not aware, So I was presenting, giving my presentation to nobody. Okay, so if it's fine for you, I'll restart the presentation from the beginning.
Please, definitely.
I really apologize, but I had not completely realized.
Yeah, I understand. If you're playing your slides in presentation mode, then you don't realize what's happening.
Yes. Okay. So let me chart.
Yeah, let's try again. Hopefully, it won't happen again.
Let me share my screen again. So can you see my screen?
Yes, we were exactly.
Now I hope that the presentation will will go smoothly, and I will hear from you if it doesn't.
Yeah, I tried to contact you via email, but maybe you haven't seen it.
Of course. Okay, I was not reading my email now.
Okay, let's
Okay.
start, please.
Okay, I apologize for this. Anyway, so what I was saying is that in this talk, this talk is about cross-lingual sentiment quantification. It's a task which departs from traditional binary sentiment classification in two main ways. Okay, so the first one is cross-linguality. So we go cross-lingual. We abandon monolingual sentiment classification, and we go cross-lingual, which essentially means that, when it's what we do when we have no training data for the language or languages T for which we want to issue predictions that we call the target languages, but we instead have training data for a number of different languages that we call the source languages. And we here, of course, assume that we have the same set of classes. The second way in which we significantly depart from traditional binary sentiment classification is that we tackle quantification and not classification. So quantification is the task which is important when we do not need to predict a class for the individual documents, but all we need to do is to predict class prevalences, so the percentages of documents in each class, which is a significantly simpler task, and because this is interesting. So cross-lingual sentiment quantification had never been discussed before in the literature, and this is why, essentially here we don't present for the moment being original algorithms. Here our goal was just to find the best combinations of existing technology to establish baselines for future work, and especially, to argue for the use of quantification algorithms for the applications in which the interest is really only at the aggregate level only, So here you will see some experimental results derived from experimenting with all combinations of 5 different quantification methods and 2 different transfer learning methods for cross-linguality that are essentially well known from the literature. So let me start with characterizing quantification. So quantification starts from the observations that in many applications of classification, the real goal is not really determining the class label of a single individual example, but the real goal is often determining the relative frequency, or also called the prevalence, of each class in the unlabeled data. And this is a task which is called sometimes quantification, supervised prevalence estimation, learning to quantify, etc. So examples of these scenarios are the following. Say, among the tweets concerning the next US presidential elections, what is the percentage of pro-Democrat ones? Again, an interesting percentages, not in individuals. Among the posts about the Apple Watch 5 posted on forums, what is the percentage of very negative ones? Here is an example of ordinal quantification, while the previous one was an example of binary quantification. And how have these percentages evolved over time recently? So, in many applications, we have this interested in monitoring temporal trends, And this is a task which has been studied across several different disciplines: statistics, machine learning, data mining, information retrieval, NLP, and it's important because it has given rise to evaluation methods, and as a consequence, learning methods, which are really specific to it. And so it should not be studied as a simple byproduct of classification. So quantification is still a fairly unknown task, and there is a lot of lack of awareness of its potential and of its usefulness, especially among potential users. And I hope that this task will, contribute to increasing this awareness a bit. So quantification essentially can also be defined as the task of approximating a true distribution via a predicted distribution. And this emphasis on distribution is the reason why, you know, a typical way of displaying the results of a quantification exercise is a histogram. A histogram that represents the different classes in our classification scheme. We have 5 of them in this histogram, and it represents by blue bars the true percentages, and the red bars the percentages predicted by a quantification algorithm. So, of course, I mean, the ideal algorithm is the one that generates red bars that are absolutely identical to the blue bars, you know. And as a result, you know, most measures for evaluating quantification belong to the class of mathematical functions called divergences, you know, because divergences are functions that evaluate how much a predicted distribution diverges or is different from the true distribution. So the basic question, you know, that we should ask ourselves is the following: is classify and count the optimal quantification strategy? So classify and count means, you know, train the best possible classifier that we might you might be able to train from your training data, and apply it to your data and count the number of individuals that have been classified, you know, in a certain class. And the answer is no, it's not the optimal quantification strategy. And the reason is very simple, you know. The reason is that while it is true that a perfect classifier is also a perfect quantifier, you know, a perfect estimator of class prevalence, it is not true that a good classifier is necessarily a good quantifier, you know. There is an example, a very simple example here with 2 different classifiers, H1 and H2, which have been tested on the same test set, you know. And here we list essentially the false positives and the false negatives that they have generated. So H1 has generated 18 false positives and 20 false negatives, while H2 has generated 20 and 20, you know. Which one is the best classifier? Of course, I mean, we should prefer H1 as a classifier because it has done fewer mistakes, you know. But in terms of quantification, paradoxically, we should prefer H2, you know, because when it comes to estimating quantities, estimating the percentages of items that fall in a certain class, a false positive and a false negative cancel each other out, you know. So H2 paradoxically is a perfect quantifier. So it has estimated our class prevalences perfectly. So this means that, you know, we need evaluation measures which are different from the one of classification. And as a result, you know, we need learning algorithms which are different. Okay, so this is the reason why quantification should not be seen as a byproduct of classification. So the need to perform quantification arises because of a phenomenon called the distribution shift, which is also sometimes called the distribution drift, you know, and which can be characterized as the presence of significant discrepancies between the class distribution of the label training data, you know, so the way that the label training data are distributed across different classes, and the class distribution of the unlabeled data. Here in this plot, you know, you can see data taken from the well-known Reuters corpus volume 1. It's a corpus of news, which is distributed across 52 different weeks, 1 year worth of data, you know, in the x-axis, you know. And the blue line represents the prevalence of a certain class E21 in this data, you know. And what you can see is that basically the prevalence oscillates quite a lot, you know, as it is natural, you know, across the different weeks. Okay, so, you know, a good quantifier is one that monitors the evolution of these class prevalences quite closely, you know. So the other 3 lines, the green, yellow, and red, are 3 different quantification algorithms that have been tested on the data. And of course, I mean, the better one is the one that, let's say, follows the blue line more closely than the other. So why does distribution shift occurs? Okay. So it may occur as a result of different reasons. Okay. So one is the fact that, say, the environment may not be stationary across time or space or other variables. Okay. So a typical example is, say, journalistic news, the class terrorism. Okay. So before a major terrorism event, you know, the number of articles that discuss terrorism is small, you know. Just immediately after, you know, the number of articles that discuss terrorism is much higher. Okay, so this is a case of an environment which is not stationary across time. You know. But other causes may be the presence of what we call sample selection bias. Okay, so the bias that we introduce in selecting our training sample. So, for instance, you know, in the process of labeling training data, we may explicitly introduce bias in the training set, so intentionally introduce bias. So, for instance, you know, when we want to model a rare event, you know, when we want to model a rare event, we tend to oversample the minority class, so put as many training examples as possible that describe the event, and maybe, you know, cut down on the number of negative examples. And a second reason may be that the process of labeling training data implicitly introduces bias in the training set. Say when we use active learning. So when we use active learning, our training set is not going to be a random sample of the underlying distribution. Is everything other than random. Okay, so in this sense, we have introduced bias because of the use of active learning. So when we introduce distribution shift, when our data, you know, display distribution shift, this invalidates the so-called IID assumption. You know, the assumption which all standard machine learning algorithms are instead based. IID means identically independently distributed. So it means that the training set and the test set are identically and independently sampled from the underlying distribution. Okay. So when this assumption fails, the algorithms that are based on it tend to fail too, you know, to lead to suboptimal accuracy. So here in this plot, you can see, you know, a number of tests that we have recently run, you know, where we plot the quantification error, so the error in estimating class prevalences on the y-axis as a function of distribution shift in the data, you know, which is plotted on the x-axis. And what you can see is that classify and count is the blue line, CC, you know, and it displays a, let's say, a behavior that we don't want, okay? Because, you know, when distribution shift grows, then its error grows too, you know. So we want to instead we prefer the behavior of algorithms that display a fairly flat line, okay? So whose error is independent of distribution shift. So why am I interested in sentiment quantification? Well, the reason is that many applications of sentiment classification, emotional classification, stance classification, actually have quantification as their final goal. You know, and this is very much true in disciplines, in a number of disciplines which are inherently interested in aggregate data and not in individual data. One example is market research, you know, or your sponsor, you know, might be interested in this talk, you know, because market research has nothing to do with the, you know, with the individual tastes of individual consumers. It wants to estimate aggregate data, you know. Social sciences, I mean, they couldn't care less about individuals. Epidemiology, they couldn't care less about individual patients, but they want to, you know, to model distributions. Opinion research too, you know. All of these fields, you know, are not interested in the needle in the haystack. They are interested in characterizing the haystack, you know. So this is also true of certain types of media. Say Twitter. How many papers about sentiment classification in Twitter, have you seen that we're interested in modeling the sentiment of an individual person, of an individual tweet? I have seen none, you know. All of them, all of the ones that I've seen, you know, are interested in the aggregate data in the end, you know. And so in all these contexts, using classification, using classify and count is suboptimal. That's why we want to, you know, work with true quantification algorithms. Here, I'm going to briefly describe 5 quantification algorithms that we have tested in this paper, in this work. One is the classify and count, the trivial baseline for all quantification efforts. And this formula basically says that, you know, if we want to estimate the proportion of the positive class, you know, in a set D via classify and count, we simply need to sum over the individual binary decisions, where H is a hard classifier that returns 1 for each positive decision and a 0 for, you know, for negative decisions. So that's a trivial baseline. So probabilistic classifying count simply improves on classifying count by replacing hard counts with expected counts, replacing, you know, binary decisions with posterior probabilities, with confidence scores, because confidence scores are richer in information than binary decisions. So it basically, S here is a soft classifier that returns a confidence score. So another slightly better algorithm is adjusted classifying count. So an algorithm that corrects the estimates obtained from classifying count according to the tendency of the classifier to generate more false positives than false negatives, or vice versa. And this tendency is something that we first estimate via k-fold cross-validation, okay? So here, this formula basically introduces the false positive rate and the true positive rate of the hard classifier as estimated via k-fold cross-validation, where, you know, this hat accent basically indicates estimation. Probabilistic adjusted classifying count is simply another variant which again replaces counts with expected counts, replaces hard binary decisions, you know, with soft confidence scores, with probabilities. And the fifth and last algorithm that we are going to use here is a method, quantification method based on deep learning, which I'm not going to describe in detail. It was presented 3 years ago. And its idea is to learn to produce what we call sample embeddings, okay? So dense representations of the entire sample, not just of individual document, okay? So embedded representation of the sample from obtained, you know, from observing the posterior probabilities generated by a classifier, obtained by observing document embeddings, and obtained by observing class prevalence estimates generated by the previously discussed 4 algorithms. Okay, so that's, you know, I hope I have given you a hint of quantification. Let me move to cross-linguality, you know. As we said, in cross-lingual classification, we want to classify documents in a target language for which we have no training data, but we want to use the training data that we have for source language. So in this case, the target languages are Italian and Spanish. You see that we have test data for Italian and Spanish, but we have no training data for them. And we want to use the help of English training data, French training data, Chinese training data. So again, I mean, the set of classes are assumed to be the same, you know, and I would like to say that this is essentially an instance of transfer learning, because we transfer from English to Italian, from France to Italian, the knowledge that we have about English and French, you know, knowledge embodied in the training examples. It's an instance of heterogeneous transfer learning, which is what makes it difficult. Because heterogeneous, because the feature spaces of the different languages are different. You know? Essentially, the approach that we will to cross-lingual classification that we will look at today consists in generating projections of the original source and target vectors into a shared language-independent feature space. So the idea is we want to look for mechanisms that allow, you know, all of the documents in different languages that are originally represented in different vector spaces to be representable in a language independent, in the same language independent feature space. And today, you know, we are going to adopt two such methods, two cross-lingual projection methods that are called structural correspondence indexing and distributional correspondence indexing. So the first one, SCL, is a very well-known method that dates back to 10 years ago, while distributed correspondence indexing is somehow more recent. And both methods share the number of intuitions. So the intuition here is that the language-independent feature space consists of so-called pivot terms, which are highly predictive pairs of translation equivalent terms, which tend to behave in a similar way in their respective languages. So one case is excellent or eccellente, excellent in English, eccellente in Italian, okay? Or masterpiece in English and capolavoro in Italian. So these are typically good pivot terms for sentiment-related applications, and there are automatic methods for selecting them. And in both methods, what they actually do is learn a matrix for each language that performs the mapping from the original vectors to the vectors in the shared space. And the two methods differ in terms of the intuitions on which their method for learning this matrix is built upon. So just let me give you quickly some experimental results. As we said, we have tested all of the combinations of the 5 quantification algorithms and the 2 cross-lingual projection methods that we have discussed. So we tested it on a fairly standard data set for cross-lingual sentiment classification, which is called Webby's CLS 10, you know. And I should like to note that any data set for a classification is also a data set for quantification, okay, because you simply need to basically count the proportions. This dataset consists of Amazon product reviews in 4 different languages and 3 different domains, books, DVDs, and music, that we have separately tested. Okay? So here, this dataset basically has 2,000 training documents and 2,000 test documents for each combination of language and domain, and it's perfectly balanced, you know. And so let's say all of the subsets are perfectly balanced. So all combinations of language domain or set, training or test set, are perfectly balanced. And it is typically the case that in cross-lingual classification, one uses English as the source language and the other languages as target. This is fairly realistic because English is the, you know, is the language where typically training data are more abundant than for other languages. Something I should like to note is that in these experiments, the results that you're going to see, we use plain bag of words. So there is no truly sentiment-based features. Okay? So the simple reason is that we simply wanted to initially establish baselines and check, you know, which algorithm basically work better without really pushing, you know, for extreme accuracy values. So, I mean, lots of improvement on the same task and data are still possible for those of you who are interested. Evaluation measures. So, as I said, I mean, there are specific evaluation measures for quantification. One is absolute error. The other is relative absolute error. The other is Kullback-Leibler divergence. Just to give an idea, absolute error simply measures, you know, the discrepancy between the predicted distribution, the predicted prevalence of the class, and the true prevalence of the class, and averages it across all of the classes. Something which is very important, okay, is the way we run experiments, okay? So if we have a test set, we can't simply establish, the class prevalences of that test set, because a single test set is a single data point for quantification. It would be as if we tested sentiment classification on a single document, okay? So because of this, we need to take the test set and generate many different samples, out of it. And we generate different samples at different preset prevalence levels, okay? So we don't just look at perfectly balanced samples, but we look also at very imbalanced samples. We take 100 samples for each such level. So each of the values that you're going to see in the table is the average across 2,100 different test samples. And, to cut a story short, I'm presenting here a table of results just for absolute error, but, for the other two measures, these are different. What you can see is that there are 10 different columns for each of the 10 different combinations of cross-lingual method, cross-linguality method, and quantification methods. And there are 9 different rows for the different setups. Okay, so as we said, for each row we use English as a source language and one different target language, German, French, and Japanese. And also we take different domains, books, DVDs, and musics. So for a total of 9 different setups. What are the results? The interesting results is that DCI is unequivocally.
Hey, Professor, you need to go faster.
Hello? Yes, okay. This is my last slide. Okay, so the answer is that unequivocally DCI is the best cross-lingual approach, and the PACC, probabilistic adjusted classifying count, tends to be the best quantification approach, although, sometimes QUANET and ACC also do perform well. So something that I want to draw your attention on is the difference between the final value on average, 0.033 obtained by PACC, and what we would obtain by using classifying count, which is 0.092. So there is, a significant decrease in error, in quantification error by using true quantification technologies instead of naive classification technologies. Okay, so this is what you're going to lose if you use just the classifier and count. And the error reduction is even higher for relative absolute error and KLD, which I'm not showing here. So conclusions, conclusions is that these are just simple initial results on cross-lingual sentiment quantification. We think that our results are reasonably good, reasonably good because it's, look, absolute error is 0.033 on average. It's as if, the true percentage was 60% and our prediction was 63.3, On average, this is pretty good, considering that we are going cross-lingual. So we are predicting on German, but we were using English data, And second, that our class prevalences are often very different from the ones in the training set. Our training set had 50-50 the prevalences, but here we are sometimes testing with 595, so which is quite different. And above all, the results really confirm that using classification, that's classification technology means classifying count in place of true quantification algorithms when class prevalence estimation is the real goal leads to degraded performance. So this is one of the most important takeaway messages of this work. Thank you very much. I hope I didn't take too much time, and I'm happy to take questions.
Thank you, Fabrizio. Very nice. We're late just because there was that technical problem in the beginning, so we'll try to catch
for
up.
which I'm very sorry.
No problem, no problem. Is there any questions from the audience?
Yeah, I have a question. Am I audible?
Yes, yes.
Yeah. So, like, is this quantification procedure going to, how does this class imbalance problem is going to impact this quantification process?
So the question, I take that the question is how much the class imbalance is affecting quantification. Let's say quantification is affected not so much by class imbalance, but by drift. Okay, so take a fairly imbalanced data set, so where the positives are 10%, and the negatives are 90%. So if you have the same proportions in the training set and the test set, you are likely to get, you might be getting a reasonably good performance from even classify and count, okay? But it is when, these percentages significantly change across training and test that you are in trouble, that you really need well-performing quantification algorithms. And essentially the fact that when your environment is unstable, or when you have built bias in your training set, you're not going to find good quantification results even in balanced data, So imbalance is not the key dimension here. Drift is the dimension, distribution drift. I hope this answers your question.
Okay, thank you.
So as you mentioned, this can be very useful for some companies that are looking at market research. And I'm aware that some companies, including Graphene, are very much interested also in the intensity of polarity. So I was wondering whether those formulas that you showed us in the beginning can also be adjusted for intensity, because you have a formula for simple frequency, one for probability. If we use intensity instead of probability, do you think we can still get meaningful results, or is that a different problem?
It's a slightly, let's say, because I have worked and consulted too for market research companies, it's, I know that they care about intensity. That's that's the problem that we would call ordinal quantification. Okay, so quantification when, well, I hope this is what you meant by intensity. So the quantification when your set of classes are totally ordered. So you're not just interested in positive, negative, but you're interested in very positive, very negative, mildly positive, mildly negative. Okay, so there has been little research, on ordinal quantification. Let's say there are only 2 papers, out in the literature, and in both papers, we were involved in this, because this is one work I did while I was in Qatar at the Qatar Research, Qatar Computing Research Institute, and the other work was done by my colleague Andrea Esoli in CNR in Pisa. So this is work that dates back to 2016. There has not been a newer work on this, but essentially, work is driven by applications, and when an application need shows up, it tends to prompt new work. Okay, so one problem with intensity was also defining a good evaluation measure, because it's not really clear what evaluation measure you should use for ordinal quantification. We have defined such a measure, which is called it's the well-known Earth movers distance. Let's say we have argued that the Earth movers distance is adequate for capturing ordinal quantification and used for those applications.
Okay, thanks very much. In the interest of time, I have to stop the Q&A session. Thanks very much again for joining us and for your talk. Very, very interesting.
Thank you very much, and apologies again for the problem. Well, I'm not really aware what the cause of it was, So, but thanks for bearing with me.
No problem. Ciao.
Ciao. Thank you.
Jing, are you online?
Oh yes, I am. But am I the next?
Yes, you are, because Hwee already spoke.
Oh, okay. I was okay. All right.
I just made you a co-host, so you should be able to share your screen.
All right. Just a minute. Oh, I think I need to. Oh, okay.
Maybe Fabrizio need to stop.
Okay, I'll stop my sharing.
Okay, thanks.
Okay. Just a minute. Let me. Okay, so yeah, so can you see the screen?
Yes, we can.
Okay. All right. Okay. So yeah, I'm very happy to be here to give a short talk about some work we did in recent years on multimodal sentiment analysis. Yeah, so I will try not to use up too much time. I think some of the other speakers may be a bit anxious now because of the delay. All right. So okay. So yeah, so this symposium is about sentiment analysis, and I think most people here are mostly talking about using text to do sentiment analysis, because most people here are NLP people, but we also understand that increasingly on the internet, on social media, people are posting a lot of images, right? So a lot of NLP people, NLP problems have now. People have realized that actually using the additional images can help us to do NLP better, right? So just to give a couple of examples, some people have studied named entity recognition and using additional image information. So for example, if you look at this post, right? Hi, I'm Xingba. You probably cannot tell what, you probably will think that Xingba is a person until you see that, this is a tweet that comes together with this post. So then you understand, oh, actually Xingba is a pet. A different problem, sarcasm detection. If you see this message, what a wonderful weather, you probably guess that, oh, the person is quite excited about, right? He's about the probably a sunny day, until again you see an image and then you realize he's being sarcastic, right? So yeah, so you see these examples everywhere. Now for sentiment analysis, of course, it's not there's no exception. So we would also expect using multimodal input to improve the performance. Now, I'm not claiming that we are doing this, we are the first to do this. Actually, you can see that I'm citing some previous work on this topic, and actually, people in the, our organizer of the symposium has done a lot of work on this. So now back to what I'm going to present, right? So what we particularly looked at is on entity level sentiment classification. Just in case there are people here who are not familiar with the task definition, you can see that given a sentence, in this case it's a tweet, but in general, given the sentence, in the early days, people would study sentence level sentiment classification, where you assign a sentiment label to the whole sentence. But sometimes the sentence may have multiple entities, and the sentiment towards the different entities may be different, right? So in this case, for example, we have this sentence that says, Georgina Hermitage is a one to watch since she broke the 400-meter T37 world record. So, so if you look at the sentiment towards Georgina, it's positive, but towards the sport, it's actually just neutral. Okay, so that's a task. Basically, you want to predict the sentiment towards different entities in the sentence. now when does the image comes into play, right? So sometimes if you have a piece of text that doesn't actually tell you the sentiment, like in this case, then you have trouble. So this is me after the Rahaina concert. So just based on the content, based on the text alone, you actually cannot tell. Now the image here actually is just the person's profile image, so that has nothing to do with this particular message, right? So so you cannot tell until you see this additional image that comes together with the text. Then you will immediately be able to tell that there's a positive sentiment here. All right, so yeah, so our task setup is that we are given a post, a target entity, and then an associated image. And then we need to predict the polarity towards the target entity. Now, the idea is quite standard. We basically need to fuse the input both from the text and from the image, right? And then after the fusion, we predict the label. Now, so the way to encode the sentence, I won't go into details here just in the interest of time, but basically you do need to separate the entity away from the context, because the target entity is important. Knowing which one is the target entity is important, right? So so in this piece of work, this was done a bit earlier. So we used LSTM to encode the sentence. So you can see in this figure that basically the text context to the left of the target entity and the context to the right of the target entity are both encoded using LSTM. But then the target entity is used to compute some kind of attention, so that we are using attention weighted version of the left context and right context to encode the text. But this is just the text part. Now, when the image comes into play, of course, a standard solution is just to simply concatenate image input with text input. But that's probably not ideal, because not every part of the image is related to the target entity, right? So, so actually, I think by now this has become a quite a standard, well-known trick or procedure to do fusion, but when we did this, I think it was I think it was still due. So we basically used the target entity to figure out, right, some attention weights, so that when we encode the image, after using standard ResNet to first process the image, after that we will compute the different attention weights for different parts of the image, so that we can pay attention to the regions that are more relevant to the target entity. So that's this part with entity attention in the model. And also we introduce something called the gating variable, and the purpose here is to make sure that it is to handle those cases where the image might be not relevant to the text. Because on social media, I think we all know that sometimes people post something, comment on something, but they actually don't have image. They're not really talking about image. So they would just post some random image in order for them to post something. Because on some social media platforms, you always have to have an image. So sometimes the image is really just a dummy image. So in those cases, you don't want the image information to have too much influence on your final sentiment prediction, right? So in that case, we introduce this gating variable to control that, right? So yeah, so these are the two things we introduced to the model on top of just simply fusing the two modalities of data. Now, if you look at the experiments, basically we use two data sets, to the 15 and 20 to the 17, which were derived from some previously used NER data sets. Now, if we just use text alone, because we want to first check whether the text encoding model that we used, which uses LSTM and then has some entity attention mechanism there, right? Whether that model is alone model actually is quite okay, right? It performs similarly to some state-of-the-art model. And then after we add in the visual part with the image information, we found that it does outperform some other choices previous work that also combines text with image. Okay, so this is the main results. And yeah, I think, yeah, so because, again, in the interest of time, I won't go into the details. We do have some further analysis in the paper, so if you're interested, you can take a look. Then I'll just very quickly go to just another piece of work which is quite related, and I think the main difference here is that we now switch to use BERT, right? So because we all know that in recent years the pre-trained BERT model has shown a lot of potential, right? So I think the main difference here is that now when we use BERT to encode the input, we have to again we isolate the target entity out, and the way we did it was to take it, move it to the end, so that we have the context where the entity has been replaced with a special token T, and then the second part is the target entity, which is moved to the end of the sentence. And then we feed it to standard BERT, right, which can be used to do the standard text alone and text only sentiment classification. And this is still target specific because the target entity has been moved to a special place. Now, when we, again, same issue as before, if we just simply concatenate the image representation with the text representation, then when target entities are different, you still use the same representation of the image, which is not ideal, right? So in this case, the example we showed earlier, right? If the target entity is the person, then you actually want to pay more attention to probably this part of the image. But when the target entity is the sport 400 meter T77, then you don't, it's not so important to look at the person's face, but probably the text, the captions here. Okay, so similar idea, we will use the target entities embedding representation to go calculate target attention. And with transformer model, this becomes quite fairly straightforward. So you treat the target embedding as a text-based target embedding as query, and then the image information will become both the value key and the value, and then that allows you to just further process the image, and then you get sort of target entity specific image representation, and then that's concatenated with this BERT-based text embedding of the input. Okay, so again, just to show you the results, so we found that this could, first of all, so using BERT can achieve better baseline without the image part, which is expected. And then when we combine BERT together with image, we can see that this model performed even better than the previous method I presented just now. So yeah, so basically to conclude, we did two pieces of work where we combined text, in this case tweets, with the images that came together with the tweets, and we found that indeed this could lead to improved sentiment classification. But of course, we actually have to carefully design some attention mechanism, particularly to reweight the image so that we could pay attention to the right part of the image, right, to help with the sentiment classification task. And we also found that using pre-trained language models such as BERT is effective. Other than that, I think the way of using the image, especially using the attention mechanism to get a attention weighted version of the image, is quite important, and that's regardless of whether you're using LSTM or BERT to encode the text. All right, okay, so before I end, I just want to acknowledge my collaborators or co-authors. Yeah. Okay, so now I'm happy to take any question you have.
Thanks, Jing. That was very interesting. Actually, those two works that you mentioned, Soujanya can confirm that we're mostly on conversational data, and the multimodal data that we were looking at were mostly facial expression. So this is actually something different, something new, something very interesting that again can be very interesting for companies as well. Is there any question from the audience?
Maybe I can ask one.
Sure.
So, hi, Jing. Can you say a bit more about the image gates, how it's differentiate whether it's a dummy image or if the image is relevant to the text? Is it a trend or?
It's trained. It's trained. So I think, I mean, okay, yeah. Let me just go back there, and it is trained. I don't have a slide showing the formula, but basically, Z is eventually Z will be it's a vector, but every dimension is something between 0 and 1. So it's like gating, standard gating variable that will later be used to multiply with the other this input. So basically, you know, if it's closer to 0, sorry, it will be multiplied with the image input. So if it's closer to 0, then you don't really rely so much on the image. If it's close to 1, you rely more. But it's not a single dimensional scalar. It's still a vector. So you do element-wise multiplication with the image input. Now, how exactly it works, right? I think because it's learned, so I suspect from the training data, maybe the model would learn that certain kind of images tend to be dummy images. I mean, but that's just my guess. I mean, ideally, we should do some further analysis to see, you know, what kind of images have triggered this, right? This gating vector to be close to 0, let's say. But I just right now I cannot remember whether we did anything like that. So, but it's learned. Yeah, it's learned. It's not through any prior human knowledge.
Okay, thank you.
So maybe a question that is in the same line as this. For the case of sarcasm, then how do you know if the image is irrelevant, or because you would have opposite polarity? So when do you know if it's sarcasm or not? Right.
So in general, I feel that because all these, I mean, so all the deep learning models we're exploring nowadays, right, are based on supervised learning in general, unless you, of course, you could inject some human knowledge. So I suspect, like, although I've not really worked on sarcasm detection, I suspect that based on the training data. So if in the training data there's certain type of images that tend to appear together with some text, and then it's labeled as sarcastic expression in overall, right? Because the scenario described is a case where we have an image, we have text, and then there's a label, and the label has to be given by the human annotator based on both the text and image. So if the model sees that certain type of image is always tend to be associated with a label of sarcasm, then it may just think that this image does contain the sarcastic content. I suspect that. But on the other hand, if there are a lot of training data where really the text tend to be similar when they're labeled as being sarcastic, but the images are very different. So maybe the model really cannot pick up that signal. This is my guess. Yeah.
Okay, thanks. Very interesting.
Can I have a question, please?
Okay, one last question.
Thank you for your nice presentation. The thing that I am considering is emoji or considered in this model as images, or it will be text?
In this case, I think the emojis will be, it's part of the text, and it will probably just be treated as a token. So although I have to confirm with, I think the first author, so whether he actually just, because emojis, if it's represented as, let's say, you know, a colon followed by a bracket, it might be even removed, right, from the input, but it could be treated as a special token. I know that there are special tokenizers for social media text that would actually capture these emojis. But in our case, emojis are part of the text. If there's some emojis in the actual image, I don't think, I mean, we don't specifically capture that. It's just part of the image.
Thank you.
Okay, thanks you. Thank you very much again.
Thanks, Erik.
We'll move to the next speaker in the interest of time. Soujanya, are you there?
Hello, hi.
Hi, hey, how are you?
Good, how are you?
Good, good.
Yeah, so I should share my screen, right?
Are you a co-host? Not yet. Let
No,
me make
not
you
yet.
a co-host.
Okay.
Okay, you should be able to share
Okay,
your
great.
screen.
Let me try. Okay. Okay. You can see my screen, right?
Yes.
Okay, awesome. Okay. Okay, so this is a bit a different topic. I mean, from the title, you can see that it's not really sentiment analysis, but there is sentiment analysis inside it, which I'm going to explain. So, yeah, so my talk is mostly on dialogue systems, and in this present talk, I will be talking about some unorthodox tasks, like which are very unconventional and not really the tasks that we use to solve as far as dialogue systems are concerned. So I will be talking about recognizing emotion, causing conversations, and inferring implicit knowledge in dialogues. So present state of the research in dialogue systems, as you can see that, of course, we all know about it, dialogue generation, like given two persons profile, you try to learn the profile and generate dialogues based on that. There is the task of dialogue state tracking. For example, you are talking to a chatbot and it's a task oriented dialogue systems. So you try to track the state of the dialogues, like if you want to book a hotel, from which area you would like to book and things like that. So these are part of dialogue state tracking. There is a dialogue act classification. Simply you classify every utterance of a dialogue with whether that is a question or a statement or or any other dialogue acts. There is also a popular task of dialogue relation extraction. So given a dialogue, you try to extract the relation between two different entities in the dialogues. This paper, I think, recently came in ACL last year, probably, called dialogue relation extraction. There is also the task of dialogue QA, like given a dialogue, you try to answer some given questions. So different to that, what our research group is working on is affective dialogue systems. Like we try to solve dialogue related problems which are which deal with affect, human emotions, human sentiment. So the primary motivation of it is to create an affective dialogue system that can converse with a human by reading the emotion. So in this particular example, as you can see that given this question, did you suffer a head injury earlier? And based on the answer, like if it is no, then potentially this is carries a positive sentiment, and the bot replies with a positive statement. But if the answer is yes, then the bot senses that it is critical, right? It's a critical issue. So the reply is vary accordingly. So based on this intuition, there can be a multiple a number of tasks. First of all, the emotion recognition in conversations, a very popular task in dialogue, in the domain of dialogues. There is empathetic dialogue generation. I think one of the speakers will be explaining about it. Let's also I mean, the recognizing emotion cause in conversations, which are not really recognizing emotions or sentiment in conversations, but the it tried to identify the cause of the expressed emotions. So we have recently released this data set called Recon. It's a data set for recognizing emotion cause in conversations. So as you can see in this example, like in a dyadic conversation, one speaker's emotion can be influenced by the emotion of the other speaker, and there can be emotion transition. For example, the person A became frustrated from angry state, and yeah, I mean, this is how the cause of the emotions can fluctuate from one utterance to another. And in this work, we try to understand that. So at in the recon, what we observed, observed the self and interspeaker influence. For example, if you try to detect the cause of the emotion, so this utterance is labeled as happy. And if you try to detect the happiness in this sentence, you can identify that the primary causes come from both the same speaker, B's previous utterances, and also the other speaker, which is A. Like, you are engaged, what a beautiful engagement ring. These are the events, these are the incidents that are the primary cause of the happiness in this utterance. So if you try to use a sentiment lexicon, or if you try to create a sentiment classifier that does not count on the context, you would probably not be able to distinguish the sentiment or emotion of this utterance number 4, right? So for that, you need to really rely on the contextual evidences and context and the cause that can be found in the context. So one of the interesting features of this data set is numerical reasoning. So as you can see in this slide, that the utterance number 12 is sad. So it's a negative emotion. Now, what is the cause of this emotion? The cause of this emotion, to detect really the cause of the emotion, a machine learning system or even a human really need to rely on the numerical reasoning in the context. For example, the seller, person B, wants the price to be 2,500, but person A really wants to buy it for only $2,000. So as the price is as the buyer cannot really offer the price he or she is asked for, the seller cannot sell it, right? So the seller is expressing a negative emotion. So to detect the cause of it, this negative emotion, you really need to do numerical reasoning. Also, sometimes, not every time the cause is contextual. Sometimes it is just non-contextual. For example, in this sentence, and the utterance number 2 by person B, the cause lies within itself, right? So it's not very expensive, it's the right area, and it has everything that we are looking for. So that is the cause of the happiness in this sentence. Now, this is the dataset statistics. So we primarily constructed the dataset based on Delhi Dialogue and IMOCAP. It contains 1,100 dialogues from Delhi Dialogue and 16 dialogues from IMOCAP. We utterances annotated with emotion cause, we have almost 6,000 utterances annotated with emotion cause. So it's it's not that large or also not that small data set. We have multiple emotion multiple emotion cause utterance cause pairs, which is approximately 10,000. And this is the data set with negative pairs. So to train a system to detect the causes, you need some negative examples so that you can train a system efficiently, right? So the negative examples we randomly created by sampling from the other dialogues or the utterances within the dialogue which are not part of the causal spans. And we formulated two different subtasks. The first subtask is causal span extraction. So given a conversation and utterance UT, the task is to extract the span from the conversational history that is relevant to the emotion cause of the utterance UT. So this is basically either you can consider it as a sequence tagging task or a question answering task, where your task is to extract the answers from the conversational history. So we used SpanBART and pretend Roberta on Squad, and you can see these are the results. And as you can see, if we use the contextual information, the performance improved. Now there is a very interesting thing, that the exact match, that means that you can exactly extract the span that is there in your evaluation data. If you consider that, the performance is very low. So this really tells us that we need to improve. I mean, there is a room for improvement, right? The second task is emotion causal entailment. So which says that given a conversation, an utterance UT and another utterance UI in the conversational history of UT, predict whether UI contains the causal span of UT. So what we did, we consider it as a natural language inference or entailment task. And we used pre-trained Roberta base and large models, and the performance, as you can see, are shown here. So again, there is really a chance of significant improvement for the future models. So if you are interested to read the paper, please visit this link, or you can just search the paper's name, Recognizing Emotion Cause in Conversations, and you can download the dataset from this link. Now, the second task that I would like to present here is DIKE, leveraging common sense to extract implicit knowledge from dialogues. So this is our recent work. Actually, the main author of this work is Dipan Noy, who is a PhD student in our group. So the main goal is to develop a rich knowledge graph from a dialogue consisting of implicit knowledge, and then use that to perform inference and reasoning. And let me just quickly explain using an example. So suppose this is a dialogue between two persons, right? And the goal of us is to select the spans, like the annotator selected the spans, and then infer the reason between the spans. For example, lost my wallet causes late, right? Missed several buses causes over 1 hour late. So so these kind of concepts and the relations between these, to establish the relation between these, needs common sense inference, right? And such knowledge can be either implicit or explicit. So for example, if you consider this utterance, you can see that it's fairly easy to detect the knowledge because it is explicit. But these types of knowledge, where you need to perform a several multi-steps reasoning, requires common sense knowledge based inference. So here are some more examples about implicit and explicit triplets. For example, in this implicit triplet, you can see that fill out the deposit form has prerequisite, like deposit has prerequisite fill out the deposit form. But in this case, explicit triplet, you can see it's fairly simple to detect. So in this work, we are mostly interested in detecting the implicit triplet. So, and there can be latent triplets also. For example, this triplet, this concept is not available in the dialogue. It does not occur in the dialogue, but the annotators had to manually include it to do the common sense reasoning. Now, this is the overall dataset size. So we constructed a dialogue. So the dataset contains almost 800 dialogues. So with over 4,500 triplets labeled with implicit and explicit knowledge. And we set up 3 different tasks. So first is the dialogue level natural language inference, where the goal is to predict if a triplet is entailed by a dialogue. Second is span extraction, like it is to extract the missing span of a triplet from the dialogue. Like we will be giving the dialogue and the subject and the relation, and the task is to predict the missing entity, okay, the target entity. And third is the multiple choice span selections, like for a given dialogue and a question, we will be giving you multiple spans to select from. So this is actually one of the branch of the subtask 2. So for the dialogue level NLI, the goal is to, it plays a central role in inferring the latent variable in a conversations. Like it can help you in reasoning, dialogue planning, and decision making. So as you can see, we used Roberta, which was trained on MNLI dataset for the dialogue level natural language inference. So the task here is to that given a dialogue and a triplet, whether the dialogue entails the triplet. So as you can see that the macro F1 score is just 70%. So yeah, still a lot to improve. And for the dialogue level QA, like given a dialogue and you have to predict the end span of a triplet. So this is the exact match score, which shows that, demonstrate that, that score is very, very, very low. We use SpanBART and Roberta. And for the dialogue level MCQ, we again observed that when the context was improved, like the dialogue was used, the performance improved. When we just provided the question, the performance was low, and the human performance is above BART and Roberta. Okay, so what is the takeaways from this work? So the takeaways is, common sense knowledge of the participants, like in a conversations, are very key to do efficient dialogue understanding, right? And it helps in reasoning, dialogue planning, and decision making. And it controls fine-grained elements of a conversation, such as avoiding repetition, asking questions, refraining from giving unrelated responses. So I have a small announcement to make. So we are organizing Singapore's Linguistic Olympiad for 6th to 12th grade. if you are interested if you are interested to participate or know someone who can participate, please do recommend him or her to contact me or take a look at this website. So yeah, so this is our lab, and this is the team that do all the work. So thank you very much, Erik, for inviting me.
No problem.
Yeah.
Nice.
Okay.
Thank you. Any questions? So for the numerical reasoning, it's quite interesting. But how do you know when, for example, increasing versus decreasing of number is positive versus negative? Because here in this example, we're talking about a cost. But if I'm talking about like a salary or a price, then it's inverted. Is there a way, like, are you using common sense to know that the decreasing of cost is positive versus the increasing of salary is positive?
Right. Okay. So very interesting point. So yeah, I agree that I mean, it will vary depending on the context, right? So I mean, this is why we need common sense. And this, you know, the modern era of Bart and Roberta, although they claim to detect such common sense in the data to infer the sentiment or emotion, yeah, usually we found that they really cannot. So in our work, we did not really focus on identifying such numerical reasoning, but instead what we tried is we tried to pick up the cases where such reasonings is very evident, right? And we ask pre-trained models like Bart and Roberta to solve such reasoning, utterances, such reasoning circumstances, and they fail. So that is what we tried to show in this paper. That yeah.
Thanks.
Any question?
Any other questions? So it's quite interesting to see how you model how sentiment changes throughout the conversation. Are you doing any other, are you keeping track of some other things like knowledge? Like, for example, in the example you gave about the wallet, are you also modeling like where this wallet is, if it's lost, if it's still with the person who's speaking? Are you looking at also this kind of reasoning yet, or it's just focused on emotions only for now?
No, I think you were talking about this task, right? Yeah. So yeah, I mean, you are right. So in this task, we are not really focusing on any emotion or sentiment. So this is really inferring implicit knowledge from the dialogues using common sense. So this is like, to infer these things, you really need to rely on the common sense inference capability of the models. So no, we are not relying on any pragmatic factor, but entirely on the common sense. Yeah.
Okay, thank you.
Thank you. Thanks for the invitation. Thank you.
Okay, next speaker is Jian.
Hi. Hi. So I share my screen, right?
Yes, please. I will make you a co-host.
Okay. Can you see my screen now?
No, not yet.
Oh. Not yet. So what happens?
No, we just we don't see it. Have you?
Okay, probably. I screen show first, then I share. See what? But I cannot. I have to share, then kind of.
Yeah, first you press the button share screen, then you select your PPT, and then you play the presentation.
Yes, I did do that, but it doesn't show.
Yeah. Do you want to try to log off and log in again? Otherwise, I don't know.
Like,
unless you
I do it again. So
instead.
It just shows that. Can you see it now?
No.
It's interesting. I've shown that.
I'm not sure what's the problem, because if you are not able to share, then you should get a message from Zoom like you don't have the like it's strange that you don't get any error message, but still we can't see your screen.
Oh, I think probably can you see it now?
Yes, we can see your screen now.
Okay.
If you can just maybe play it full screen.
Yes.
You can...
Yes.
Yes.
So
okay, perfect.
you can see it now, right?
Yes.
Okay. Hello, everyone. I'm Jiang from A-Star Institute for Infocomm Research. And thanks, Erik, for the invitation. My pleasure to give a brief overview of the research and the practice on sentiment analysis in my group over the years. So I gave a list of work in a so-called tapestry. So basically, we started work, my group started work back in 2009. I still remember that I invited Professor Jing Weber, who is has a earliest work on sentiment and subjectivity. Remember that she told me that when he published back to 1990, she was questioned why you work on such a topic. But now, 30 years afterwards, just look at the list of speakers in this symposium, we can sense that how hot the topic is now. So with the inspiration from Jian's talk, one researcher in my team started to look into sentiment similarities and supervised a PhD student then. And afterwards, there's another team member started to look at aspect-based sentiment analysis, focusing more on aspect and opinion target recognition. Roughly around the same time, back in 2014, we started to look into applications. Although the path is not straightforward, but eventually in 2016, through the joint laboratory of Institute of S3A and Baidu, which I'm in charge of, we are able to launch a project in 2016 to release the technologies with industry strengths, with a satisfy rigid performance requirement, leveraging large-scale text collections. And we are able to release it for multiple applications over multiple product platforms for recommendation reason, for generate recommendation reason, user opinion tag, also provide support the online tracing, the online impression of public figures. Besides command opinion extraction and classifications, we also, produce another relevant topic. I saw someone here in this symposium are going to talk about financial sentiment analysis. I think probably make it broader, we can consider it benefactive and malefactive news event detection with, of course, financial is one of the popular impact such a objective news can create. And the work itself also has a target, what's the good for and bad for entities. So, well, from 2016 to 2019, we have a collaborate with a government organization. We look into deep learning models on sentiment classifications and sarcasm identification. And we also apply them to Singapore social media multiple platform with sentiment semantic analysis. Well, the semantics analysis, including the semantic topic and the name entities, which serve as part of opinion target terms. So we produced, instead of those using a lot of online public tools that on name entity recognitions. But what we produce to our customer is a semi-supervised framework that allow customers with a minimum data to adapt to their own data. So we're able to show that using about only 10% of data that is able to recover the performance to the source to the source data as the same performance of the source data. So I will give a brief elaboration of each of them. So early stage, the sentiment similarity back in, for example, our ACL 2013 papers, pretty much, it's a word level polarity. So we leverage on the probability hidden emotion vectors. So that means that the emotion are not predefined with numbers in terms of numbers and the type of emotions. And we are able to, using this probability model, we produce the sentiment similarity instead of calculate sentiment similarity, but in fact it's a semantic similarity, like those measures like PMI, LSA, and those leverage on conventional word vectors. The 2016 aspect-based sentiment analysis, our work is among one of the earliest study on this topic that leverage on deep learning work. So that was kind of hybrid models. So we leverage on CNN probabilities and RNN probabilities in the hybrid models for aspect category classification and opinion target recognition. And even compared to our own strong baseline, which saw the best performance, top performance back to 2015, this work is still be able to show significant performance improvement. So the deep learning power are able to demonstrate at this stage for this task. In terms of sentiment classification and sarcasm identification, so one of, over the years, for the conventional sentiment classification, sentiment lexicons are very valuable resources. However, it was kind of a difficult, challenging, it's kind of inherited challenging to be incorporated effectively in deep learning model. So this work is come up with a new attention-based neural architect to be able to incorporate them effectively, which produce significant better performance over the sum-eval data set. Well, sarcasm identification is actually a kind of a research by request from our founder, our user. So, we produced proposed attention-based neural models that instead of a conventional neural attention scheme, which only focus on relevant words and subphrases. So the new model capture the word-word relationship. Thus, it able to explicitly model the contrast and the incongruity. As a result, it's able to show the best performance over 6 public data sets. Interestingly, that the work is just published before preaching model, and so we as a result that we also tested out on the to compare it with BERT. Fortunately for this, I mean, for our final project review, it's not conclusive that BERT is necessarily dominate, at least with some of our project data set. It's not the case. Our approach still show more effective. And here is some application. So I quickly go through. So these are kind of a recommendation reasons that used for personal assistant. For example, recommend the chairman branch for the famous Peking duck. So the reason is the chairman branch is the earliest and the longer history, better service. So these are all extracted from user commands. And it was also used for support mobile search and Baidu's online to offline app. For example, through the opinion tag. So the famous Heidi Lao, the steamboat, because it get good service for more than 100 times and test good for more than 30 times. So it was it was recommended through Baidu's mobile search to the users. And it was further released through Baidu's OpenAI platform through 2 operators, including sentiment classification and command opinion extraction. And it was used for public figure online impression tracing by analyzing blogs and tweets and so on. So these are all quite large-scale deployments upon release, attract in a short period, attract about millions of page views per day or API calls per day. So besides sentiment classification and opinion target extraction, so this is what I mentioned, that the entity-based benefactive and malefactive event detection. So we extract, you see, what's the companies and the products or key persons in the news. The news are really good for or bad for. For example, Deloitte, the first news title mentioned Deloitte maintains Baidu buying rate with a target price of US $261. So it's to Baidu it's a positive, but to Deloitte it's neutral. The second title, Siri's ability to recognize foreign languages surpasses Cortana and Google now. Of course, it's a good news for the product Siri, but negative news for Cortana and Google now. So there's a piece of work that I mentioned that besides the semantic, well, the sentiment, we also generate the popular command. So it's a kind of sentiment-based summarization. Well, we all see that the Sunnyvale benchmark, the performance is pretty low. Luckily, with the project data, we are able to achieve a satisfying performance, almost close to the performance that we produce for our industry partners. But I would say that over this kind of a lot of studies and a lot of large-scale deployment, there are still a lot of research to be done. That I still remember that one of our founders, I mean, even that we present our performance, they still consider that sentiment is unreliable. But you really need to look at the specific situations. It's complex situations. And of course, there are a lot of research still to be done. And some of the topic we already look into, for example, dialogue level sentiment analysis. And we probably have some recent release later this year. And some other things related to dialogue, like multiple multi-turns, that we have some related work as well. So it's just when I preparing these slides, I just realized from our starting point, it's about 1 decade. So it's just my pleasure to share the talk, and in the memory of my co-chair, program chair at 2009. And so these are list of publications over this topic I mentioned through my slides, and some project members I would like to acknowledge for the various applications that we have built over the year. So that's the end of my talk.
Thank you. Very nice. A lot of applications you guys are working on.
Yeah, we are from A-Star. By
questions?
default, we need to, you see, build applications.
Right.
Yeah.
Any questions from the audience? So in the slide where you were talking about sarcasm, you said that it's difficult to take into account lexicons. So I didn't get if in the end you managed to inject some external knowledge in your deep learning model or not.
Oh, these are 2 pieces of work. One is on sentiment classification. What I mentioned is that, you know, we have a lot of even large scale sentiment lexicons that we, you see, it's a valuable resource. So yeah, that is attention models to incorporate that. Before that, it's not straightforward. There are some inherited difficulties, you see, without the context. It's difficult to incorporate in the deep learning model effectively to show benefit. So another piece of work is on sarcasm identification. So that is 2 pieces of work.
Okay, thanks. Okay, in the interest of time, we'll skip to the next speaker. Thank you again, Jiang.
Welcome.
So next speaker is Frank, who is already a co-host. He's gonna talk about. Hi.
Hi. So I will try to share my screen.
Yes, please.
I hope you can see my screen now.
Yes.
Okay, great. Thank you, Erik, for inviting me to this symposium. So today I'm just gonna talk about financial sentiment analysis and show some small experiments here. So there are 2 motivations that I approach this research project. First is that you can see already in some talk conferences, like people present their model like with this table, which I blurred because it's still in review. The people put a table and their model kind of in bold fonts outperform the baseline models. But just like Fabrizio just presented, say if you have a classifier that make the same amount of false negative and false positive, and then if your measure is prevalence, then you have a perfect classifier, and you may not even be able to, realize that there is an error in the classifier. So what I want to do is I want to compare those methods with a bit more information other than the performance measure. Second, the motivation is that since you have those instance level performance results, so if you look into the overlapping errors, you will be able to analyze that population, which is the errors that all of the models fail to predict the correct sentiments. And then I hope improvements on this population of samples can be generalized to many sentiment analysis methods to improve them. So here is the data sets. We curated a stock tweet sentiment data sets for the finance domain. One good thing about this professional platform stock tweets is that they have the users can actually post the tweets and at the same time label them as bullish or bearish. So that I hope this can be used as ground truth. Of course, some users don't label them. And then what I do is that I just fill out those unlabeled ones and use those labeled ones. So sorry, in total, we have this trending positive of like 10,000 data and trending negative 3,000 and test positive 4,000, test negative 1,000. So in total, we have around 20K of data, but different token or different words is like 40K. So we can see that it's not, so every single twist is not that very long. So, and I visualize the sentiment analysis results. So here you can see the white bars are actually false negative and the black bars are false positive ones. And I experiment with 8 methods for the coverage of all of the common sentiment analysis methods. So we have this opinion lexicon from Bin Liu's work and SentiNet, and a domain-specific Lofgren and McDonald dictionary. So these first 3 are lexicon-based methods. And also we can use SVM to do sentiment analysis and fast text. And I have this by RSTM and the sentiment state RSTM and BERT, which is pre-trained language model, and I fine-tune it with the training data, and then I test it. So here is pairwise correlation I have for those 8 methods. So from the left side, you can see, I want to draw attention. This is like the correlation between the performance results. You can see that here is like a cluster, I would say, fast text by RSTM, SOTM, BERT, or deep learning or machine learning based model. They tend to, you know, have the similar behavior. For no matter it's correct or wrong, they predict the same labels for the same instances. And also this here you have the lexicon-based one, not that strong correlation as this deep learning one. Yeah, and the right side we have this correlation matrix. The upper triangle is for the positive true ground truth positive instances, and this lower triangle is for negative one. So you can see this one is generally the upper side is darker, which means for positive stock tweets, the different methods agree more, but for negative one, which is potentially more difficult, there is less agreement between different predictions from various methods. So I still show you some performance. Like with this MCC, which because you see that positive samples are like 3 times more than negative ones. This is like naturally unbalanced data sets. So I use this MCC, which is a measure good for unbalanced data. And I have F1 and accuracy. So you can see you cannot really rely on a single measure.
我刚给那个 sentiment analysis 的那个 talk 就很麻烦，我觉得。
I don't know what's happening, but I guess I can take questions later.
Continue.
Okay, so yeah, I would say if you try to balance between those three different metrics, I would say S3M is best performing one. BERT also, you can see that even MCC and F1, BERT is very close to S3M, but this actually means this is some feature from finance dataset, because I also experimented with Yelp dataset, which is like normal movie review, business review, and all of the MCC F1 accuracy will agree. So that means the dataset is actually more difficult. So then what happened to the common errors, which is around 400 problem child, I call them, because all of the 8 methods failed. And I look into the 400 samples and I want to find out what's happened there. So I conclude with 6 types of errors: erratus mood, rhetoric, dependent opinion, unspecified aspects, unrecognized words, and external references. So what I do with some of my collaborators, we label the test data with this type of arrows, and we want to see the concentration. So actually, erratus mood, it's not just restricted to financial data, because in this Yelp data, also in the arrow examples, you have far more concentration than the text data. So maybe I explain a bit more about the concentration. For example, you have 10 samples, and 2 belongs to this type of arrow. And then maybe in the arrow set, you have like 5. You have 5 arrows, and 4 belongs to this arrow, which is 80% concentration. So this higher concentration actually means this is some feature that is related to the data set. So actually you can see that for the stock twist data sets, nearly all of the 6 type of errors have higher concentration comparing to in the test data sets. So I give you some examples here. For example, imperative mood, which belongs to erratus mood data. For example, 2 negative articles paid for by short sellers, don't believe them. So it actually tells you to don't believe those negative articles and don't believe those short sellers. But I guess this negative and short, all those kind of negative words caused all of the models, including the lexicon-based one and machine learning-based one, to predict wrong on this case. You have rhetorical questions like what recession, who buys at 2000 with a question mark. So those ones like recession, which is negative, but what recession, and a rhetorical question actually means the speaker don't believe there is a recession, so it's actually labeled as positive. And of course, unrecognized words like the stock form, the head and shoulder. Head and shoulder is some technical jargon, but if you don't have that in your lexicon, or simply look at head or shoulder, don't really give you the sentiment label. So yeah, those are examples from the different error types. And if you want to know more detail, you can look at this article from this link. And I will thank you and take your questions from here.
Thank you, Frank. Any questions? So do you have any recommendation on how these problems could be solved in the future, like maybe using common sense or different kinds of knowledge representation plus deep learning?
Yes, I guess like Soujanya also presented, there's numerical reasoning. I didn't put here, but I guess it belongs to external reference. For example, you're talking about stock price tomorrow. then the only way to know it's bullish or bearish or it's negative or positive is to know the price of today, which is external reference. So definitely you need reasoning and the external knowledge sources. So I mean, actually, we discovered these 6 main type of arrows, and I think if you have any components that can, so for example, you have a component that's tackle with rhetoric question, and then you put this on top of the any method that I experiment here, you should have some marginal improvement, I would say.
Okay, thanks. Okay, in the interest of time, let's skip to the next speaker. Thanks again, Frank. Next in line is Zhaoxia.
Yes, I'm here. Okay.
I tried.
Wait a minute. Whether I can. Okay. Okay. So, would you please let me share my screen?
Yes, you are a co-host.
Okay, let me see. Okay. So, can you see my screen?
Yes, we can.
Okay, and you can hear me, yes?
Yes.
Okay. Okay, thank you very much, Erik, for your invitation. Okay, good afternoon, everyone. My presentations, the title is Multi-Level Fine-Scale Sentiment Sensing with Ambivalence Handling. So once I give another similar talk titled The First Step for Human-Like Language Understanding, they have similar content. So my sentiment analysis research, especially latest work, reflects the effort, towards realizing human-like language understanding. Okay, so let me show this one. Oh, sorry. Okay, so today's talk includes the following 4 sections: from enhancing learning-based method to multi-level fine-scale sentiment sensing. I will briefly introduce these 4 sections one by one. Okay, here you can see about how to enhance the existing learning-based method. There are a lot of enhancement strategies can be used. Today, I will mention negation handling, emoticon handling, and feature selection. Okay, here you can see, as shown in the table, the performance of all the 3 learning-based methods are improved by the proposed enhancement. So next, I will introduce some further work we have done on feature selection for learning-based method. Here you can see the research result about feature selection are shown in these figures. See, a clear relationship between the performance of learning-based method and the number of features selected. Here you can see. See, so there is always an optimize the number of features used for obtaining the best performance of learning-based method. See. So about our contribution to learning-based method, we first present a very clear relationship between the performance of learning-based method and the number of features selected. We also prove that the proposed enhancement can improve the performance of learning-based method. So next, now comes to the second section, fine-grained sentiment and emotion classification. Just as I mentioned just now, the learning-based method have the capability to learn and to handle big data. And we can significantly improve the performance of them by different enhancements. However, whatever learning-based method we use include deep learning method. Most of them are black box method. They are not human-like processing and not explainable. So in this section, I will introduce some research, include my early work and recent work with my collaborators, which indicate our efforts towards human-like language understanding. Okay, so about fine-grained sentiment and emotion classification, we have invented a series method which have been patent filed. or paper published. So I will briefly introduce them. You can see this page shows the first patent filed. I would like to mention here is Sentinel. So you will find later, we always give a surname to our patent method. So Sentinel is with multiple module design. This is a methodology. So the system not only output the aggregate level of sentiment, for example, positive, negative, and neutral. So the method design enable the system to output fine-grained emotion of positive or negative emotion. For example, as shown see in this figure, yes, the negative emotion here, anger, anxiety, and sadness, and so on. So now I will introduce other fine-grained sensing patent techniques, chips. So in chips invention, it is still, you can see, multi-module design. This is also the methodology. So the system not only output the fine-grained sentiment and emotion. So the aspect or object, considered. For example, here you can see, yes, there is a submodule which performs topic and object identification. For example, if I say, okay, I love A, but I dislike B. So in such a statement, towards aspect A, it is positive, but towards aspect or object B, it is negative. So in addition, you can see the multi-language or mixed language processing is proposed and designed for this patent. So now I will introduce the overall idea of the proposed method. So the initial idea is to mimic human understanding language process. So I use myself as a case study. English is not my native language, but I can understand it without any difficulty. If I understand or know the word and the structure of language, okay, it's easy for me. So I will pass or decompose the sentence into smaller components of part of speech. For example, noun phrases, verb or verb phrases, prepositional phrases, and so on. And also, decompose the sentence to the smaller components such as subject, predicate, object, complementary, and so on. So beside the decomposing or passing sentence to part of speech sentence component, knowing the words, phrases, and different sentence components. So I must know the knowledge of how to handle negation, question mark, how to identify some indicator words such as very, slightly. So it's amplifier and reducer. See? So therefore, the sentiment sensing algorithm, we designed here according to what and how we understand a language. So this is why I call our sentiment analysis engine human being language understanding simulator. So here you see, you may be interested in why I changed the name Zhaoxia language understanding simulator and replace the initial human-like language understanding. So there is very interesting. There is when I present the patent document to our management. So there is a evaluation management named Travis. He's very interesting guy. He always questioned me again and again. He said, okay, he never used the same language understanding process to understand the English. So I explained to him, this is the process that I understand the English as well as English, as well as a Chinese language. But he argues, he never, used the same, language understanding process since, he maybe native language is English. Then so I say, okay, I changed the name to Zhaoxia language understanding simulator. Since then, he never questioned me and happy to support me. So interesting. Okay. So let's continue. So now comes to the third section, intelligent sentiment sensing, consider ambivalence handler and sarcasm detection. So it is typical hybrid method. Here you can see this picture shows the details of the proposed intelligent sensing technology we designed, which is a patent file. So yeah, you can search it. It is typical hybrid method. During the limited time, I will only mention maybe one submodule or subfunction, for example, sarcasm detection. So here you can see about sarcasm detection. According to common structure we find for sarcasm detection, we design rules for sarcasm detection. I also do some research on learning-based method. And the learning-based method do help me, help us to build the knowledge about design rules for sarcasm detection. So in fact, we find more than 10 rules and structures, and I showcase here one. Okay. And this page shows before I left A-Star and joined SMU. See here, you can see in 1 year, there have been more than 10 companies who sign evaluation lessons or commercial lessons about our patent, file technology, the sentiment system. Anyway, now comes to the first section, multi-level fine-scale sentiment sensing technologies. So that this is recent work. Yes, reflect the effort, to realize human-like language understanding. So the method includes the two sequential main modules. One, classify sentiments with ambivalence handling, include sarcasm detection. And the second, identify the multi-level fine-scale sentiment. See? Okay, so here, figure one, you can see, illustrate the idea for ambivalence handling. So figure 1C also perfectly represents the human understanding of the relationship between positive, negative, neutral, and ambivalence. So here you can see we present positive, negative, neutral, and ambivalence in 4 quadrants, as shown in figure 1. See, low dimension, enough. So we define the ambivalence sentiment as sentiment output, which include positive sentiment as well as negative sentiment. See, here you can see, I think I already make it very clear, so no need to details. Okay, so next, now I will introduce how we realize fine-grained multi-level sentiment. For example, how we identify slightly positive or strongly positive. So here you can see, we define the stress level tuning parameter, ABC, just like what human beings have done, human being include myself. So how we handle enhancer? Oh, very much. See, and the super, how we handle the reducer. See, so this is what we design. Yeah, the multi-level of fine-scale sentiment. Yeah, so identify by using what we define stress level tuning parameter ABC. Okay, so here, figure one shows the main idea of identify the multi-level fine-scale sentiment. So table 1, here you can see, so K equals 4. It is 4-level positive sentiment output from slightly positive to strongly positive, level 1 to level 4 as shown in this table. So in fact, we can select the different K according to the request from our industry partner or according to different problem we want to solve. I remember that one of our industry partner mentioned to me that they prefer 5-level positive, level 1 to level 5, a positive level, and 5-level negative. So in fact, we can select equally spaced, or interval, or unequal spacing if needed. So in this slide or in the paper, we use we use equal spacing. Okay. So now I finish my talk about future work. We will continue our effort towards human-like language understanding, or true language understanding. Okay, so okay, thank you, Erik, for the invitation. Thank you all for attending my talk. So, any question?
Any questions? I was just wondering if, like in the case of sarcasm, the rules that you found are similar from language to language. Like, for example, negation, the way we express negation is similar in different languages. Are those rules language independent or are these
similar?
Language specific?
Here you can see this one. You can see when we handle the ambivalence handling, so there already indicate some rules. But the rule we design here, you can see here. We, in fact, from the learning-based method and from the manpower, we analyze so many data. Then the more than 10 structure and rules for sarcasm detection are derived. Here I show one. Just now, your question is whether the similar to similar between the language. So I only can answer you from Chinese to English or English or Chinese is similar rule for English and Chinese. Because I don't know other language, for example, Japan and Korea, I don't know. But here you can see for English is similar to the Chinese language. Chinese language also, this rule also, I mean, suitable for Chinese language. But we designed this one, you can see, we designed this in English language, but can, also suitable for Chinese language.
Right.
Okay.
Thanks.
Oh, okay. Thank you very much. Okay.
Thank you for your time.
So I need to stop sharing, yes?
Yes.
Okay. Stop sharing. Okay.
The speaker is Haiyun.
Hi, Erik.
Hi, bro.
Can I share my screen now?
Yes, please.
Kindly add me to the co-host, please.
Oh, right. I forgot. Okay, you should be good.
To mute myself. Okay.
Okay, can I be seen?
Yeah.
Great. All right, good afternoon, everyone. My name is Haiyun. I came from Alibaba Group, Singapore, specifically Double Academy. As a research academy, we are conducting research in fundamental NLP in multilingual setting, especially in Southeast Asian languages. And as a company, we're also conducting application-oriented research, such as sentiment analysis. So that brings the topic of my talk today. And so I'm introducing a novel task in aspect-based sentiment analysis. This work was published in SAAA last year. I'll first give a throwback to the aspect-based sentiment analysis. Then I'll present a new task for the ABSA. In terms of ABSA, we have so many concepts, but to conclude, let's just give one example here. Waiters are friendly, but pasta is simply average, not worthy. So all in all, what we are trying to do is to solve 4 problems. What are the targets are we talking about? And how is the sentiment for this target? And what has contributed? Why is it causing this sentiment? And which category does this sentiment falls to? So if we put them into more abstract form, so the first word comes to the aspect term. So we have to have an explicit mention of the terms appearing in the text. Then the how, what is the sentiment polarity, positive, negative, and neutral. Then why, opinion terms, usually comes with emotion expressions expressing why has causing this sentiment polarity. And finally, the aspect category. This is pretty much based on the domain we are talking about. Say in the example here, we are talking about food and beverages. So for the pasta, then it will become service for the waiters. So all in all, like through the history that as we could see from the top 3 rectangles on top are the targets we are looking for the 4 tasks. So the what solve the solves the extract circle under the aspect and target term rectangle. Then the how solve the sentiment polarity under this target. And the why is basically extracting the opinion terms of the target is talking about. Then the which talks about the categories, which is an aspect or target category to categorize them. And the sentiment circle here basically is aligned with the aspect term sentiment. So in the middle hyperplane is the initial tasks where all the ABSA tasks are focusing. Then in recent years, they were more on the a combination of either of the circles. As you will see, given a sentence, we need to extract both what are the targets as well as the sentiment polarity. But this is not usually not enough. I don't know if the panel is obstructing the slides or not. No.
Yeah, we can see the new pieces of text appearing.
Okay, great. So so the triplet basically is talking about like given a sentence, we don't tell you anything. Just give me the aspect targets, the polarity, as well as the opinion expressions, what has contributed to this sentiment polarity. So the first task I'm gonna introduce is talking about aspect sentiment classification. It's a first circle under the target here. I give one sentence, the red apple released in California a few years back was my favorite. So very intuitive. We want to learn the sentence semantics from this aspect red apples. So a very early work of ADAE LSTM based on the LSTM as well as attention mechanism has solved two problems. The first is aspect. It is specifically used within the sentence context. Then the word embeddings for this red apple is context aware thanks to the attention mechanism. Then if we go forward of how to extract the raters plus sentiment polarity, then we have our second task is appending the sentiment classification with the aspect extract. Usually the, given an example here, the AMD Turing processor seems to always perform much better than Intel. So the first task is about extract. It is usually formulated as a sequence tagging. So we have the BIESO to tag each of the terms. Then the second task, we want to classify for each of the aspect terms. We need to know the positive, neutral, or negative. So how do we combine them? A way was to having a unified tagging. So basically for each of the extract tags, we could have three variants, namely BPOS, BNEG, or BNeutral. In this way, the extract task and the sentiment classification tasks could be combined. This picture shows the overall framework of the model, but we are focusing one time step. In the bottom, we have X2, which nominates the pre-trained embedding. It usually a lookup embedding, followed by the target prediction here, LSTM, bidirectional LSTM especially, for learning to classify the targets boundary for our aspect target. Then the unified prediction. As in the previous slide we have introduced, we also want to classify the targets with the sentiment priority. Then we have the sentiment consistency module, as in SC here, which I'll introduce in the next slide, followed by the boundary guidance, which is using the boundary information to help us have a better classification of the unified prediction, followed by the appealing expression. If we decompose this module, let's say the first one is SC, sentiment consistency. The intuition behind is, for example, in a sentence, I love the fugu fish sashimi. The fugu fish sashimi comprised of three terms, but is one aspect target. It won't happen like if we have fugu as positive, but fish as negative. This should not happen. So what we are trying to achieve is to have a consistent polarity of the terms. So what is developed was a gating mechanism we are like sending the signal from the previous time step to the current step to coerce. They have aligned representation. Then the next is the OE, appearing extraction. The intuition is targets usually co-appear with appearing expressions. So we have a third labeled source for the target of whether in between the of the neighborhood of the target, whether have opinion terms or not. Then the next is a module is about BG. It is a boundary guidance. What it means is that if we have a token named as B, namely it is a beginning of an aspect target, so the unified tagging could only be B pos, neutral, or B neg. So you should never go to like it is in I pos, I neutral, or I neg, or maybe out. So based on this intuition, we have created a transformation from the signals which we already have in the LSTM target classification for the boundary sent into here for linear transformation to make sure the output could only result from these three candidates. Then we merge with this unified tagging to have the final unified tag sentiment classification. This is the overall picture. Each of this block is a time step. Then the overall for the loss function is a typical cross entropy. And the general loss for the whole training objective is LS. S stands for the unified tagging. T stands for the target itself from here. And the O is the one have the opinion expressions. Now with this, we have solved these two elements, but our task has focusing on the triplet extraction. Like if we have talking about three elements, so what are how many steps for us to get it? So intuitively, we want to extract all the elements one by one, then we could pair them up. Then you will have a triplet, the proper one. So our step will break to two stages. Stage one, extract all the elements. In a framework shown here, on the left-hand side part is a typical unified tagging, which introduced in the previous module. On the right-hand side, in the red rectangle, is the about opinion terms. Specifically, we have developed the employed the GCN, graph convolutional neural net, to encode the syntactic relations between the aspect targets and opinions. Then we also developed a target guidance. The intuition is that opinions usually modify targets. So we want to use the opinion representation to help the target to guide us, extract opinion representations. Follow, then we have the bidirectional LSTM. This was simply to encode the sentence semantics. Then we have this signal to classify whether a term is the opinion terms or not. After this stage one, we will have a bunch of candidates. Say on the left-hand side is the aspect targets in unified tag. On the right-hand side is the opinion terms. So we want to make couple between each of it. So we have a candidate pair pool. So each of these aspects will pair up with the all the extracted opinion terms. The next will feed them to a extract their representation from a sentence. And this sentence we have develop a specific positional index. Basically, it utilizes position relation between an aspect target and opinion expressions. So the difference in terms of word between these two objects will become the number of our position index. Then here, for example, the waiters are nice and the sashimi is out of the word. The waiters is a target and nice is our opinion term. They were two gaps apart. So we have the two denominating both of these terms. Then this will be fed to a matrix, which is randomly initialized when we'll look up for train and look up for its representation. this positional embedding then will be concatenated with a pre-trained word embedding. Next will be fed to a bidirectional LSTM. Then the target as well as the opinion terms, the representations will be averaged and concatenated, then sent for binary classification. So more specifically, we in this sentence, we have weights plus, which is unified tagging. Then we have nice opinion term. Then in these two weights and sashimi and nice and over these two targets and two opinion terms, we could have 4 different pairs. Then after this classification, these pairs owning the 2 correct ones will remain. For the evaluations, so we conduct the evaluation in 3 folds. The first is about evaluating the unified tagging, which is about aspect extraction plus the sentiment classification. As our intuition that opinion terms will help the sentiment and aspect extraction. So as you could see that our proposed method has performed better than the previous aspect extraction as well as sentiment classification. And vice versa, we also believe the aspect information will also help to extract opinion terms. So right, then finally we have our as you can see from here, the opinion term extraction, and it has also helped the intuitive opinion term extraction improve a lot with the aspect information. Then lastly, we have the final results of the pair and triplet setting. So the pair, we mean we only having the sentiment aspect as well as the opinion terms. And for the triplet, we having the aspect target plus the sentiment polarity as well as opinion terms. As you can see, our proposed method has outperformed all the state of art. And this has basically set up a benchmark for this triplet task. And we're lucky to see that after this work, there were already 3 pieces of new work following this track working on this sentiment triplet extraction work. As for the future work, we believe it is quite intuitive. If we could have the triplet task, why wouldn't we have the quadruplet? So we could like add 1 more element of the sentiment, aspect category. So we could have something like, given a sentence, we could have weights plus sentiment polarity plus the opinion terms as well as the categories. And luckily, we are currently annotating a large data set on this task. So this one reason that previously I don't do this quadruplet in one shot is because it's lacking such a data set. So we are currently working on to annotating a big, large enough data set for this quadruplet extraction. And this brings to the end of my talk. So the takeaway, there are 4 subtasks in the ABSA, and second is about sentiment triplet extraction.
Thank you.
And questions?
Any questions? So have you considered using your algorithm also for concept extraction? Because using the same kind of approach, you are able to extract like 3-word concept, like for example, fugu fish sashimi.
Right, absolutely. We believe, so currently the ABS is basically working on a token level, but as we know that in our communication, everything was based on the fundamental, was not word, it is not word token, it is concept. So a better way to formulate the target is to formulate as a concept itself. So I definitely think the fundamental thing about the ABSA we're working with should start from concept, the basic element.
Is your system able to handle anaphora? So do you have any sentences in your data set that contain pronouns? Like in those cases, can the aspect term still be correctly linked to the sentiment or not? Are you handling the problem yet?
Yeah, good question. Like for the moment, because every ABSS task was based on the semi-val 14, 15, 16, it is a rather limited data set. And first, twofold. First, the volume is more. Second is the context is very short. Each of the entry was like multiple words. You don't have a context in the review sense. So currently in our data set, we are trying to annotating is trying to have a larger context. So it could be a review level, like up to 100 terms in a review. Then with that, it occurs many times in the review that different terms were mentioned and the opinion terms were referred to much more before the current sentence. So I think this definitely brings the task of not for disaggregation necessary for this ABSA context.
Okay, some idea for future work then.
Yeah.
Okay, thank you very much again.
Thank you.
And is Yinping here?
Hello, hi.
Hi.
Good afternoon, everyone.
Good afternoon. I just make you a co-host, so you should be able to share your screen.
Yeah, sure. Are you able to see my screen?
Yes.
Oh, okay. Hi. Thanks again, Erik, for inviting me to share this piece of very recent work that we did. For a context, I think is relevant to everyone's life. This study has a very application-intensive perspective to look at how, in a global scale, how people reacted to the COVID-19 through its development. So, but I will still share a little bit on the technology behind, and then I'll move on to discuss the important learning points that we could find from this research. And then at the end of my presentation, I will discuss a little bit about the current work and some key takeaway messages that could open up for new research. Okay, so first of all, I want to thank two pretty large teams who have supported the work that I'm presenting today, especially Dr. Raj Gupta, who is also here in the audience, which has been working with me for the past several years. And we have also a large team from all the way from linguistics, psychology, and engineering to support all the data acquisition, analytics, as well as interpretation work. So our research has been supported by several grants. One of them is from the NMRC COVID-19 emergency grant on social media analysis. This work has also been a collaborative effort with communication scientists and the team led by Professor May-O Lin, also from NTU, and also the team who has supported a lot in the interpretation aspect of our sentiment and emotion analysis. Okay, so I will start by giving a introduction of what we do here to give you a context at what level of technologies we applied for this research. So overall in A*, so I'm from the Institute of High Performance Computing. So we have this group called Affective and Social Intelligence, recently grown to be about 14 researchers and engineers. And then we have a relatively balanced effort, both in terms of building new technologies, as well as have an equal weights in terms of applying these technologies, because at A*, we do, as part of our mission, to support public agencies and the companies to look at how we can make sense of this data and technologies for some kind of real-world implementation and recommendations. So our most recent range of technologies range from a sarcasm detection engine all the way to a more end-to-end data acquisition plus results visualization engine. And then we have worked relatively focusing on the space of industry partners from media, consumer, as well as hospitality. So you can imagine basically all those industries and public agencies who have a lot of interfaces with general public, consumers, and commuters. Before I mention the two base technologies we applied, just a little bit of differentiator here is that one aspect of the approach we apply for sentiment analysis as a general, as Erik Cambria call it, a big sweet like a big sweet case. It covers so many aspects. But this group at A*, we relatively have a more emphasis in digging a bit further into the social science concepts and principles, for which I have like half of my training is coming from social behavior and management science. And it just allow me to illustrate that the pertinent psychological concepts we view the space of sentiment emotion analysis, they are actually threefold. The first area, I think everyone in this audience will be very familiar with so-called categorical view of emotions. So this is the most intuitive view of emotions. And the one famous view of emotions, for example, by the authors, Plachik, and they talk about the various emotions can be combined. So there is also an ongoing and never-ending debate among psychologists whether there should be a basic emotion, and if there's basic emotion, what criteria do we apply for basicality? So assuming that psychology wouldn't settle for that, but as technology researchers, we still move on. Still, nevertheless, this is a very important and very fundamental concept for researchers and users to understand emotions. The second category or school of thought about emotion is on the so-called dimensional model of emotions. So this basically is not really discussing about emotion per se, but looking at the characteristics of emotions. So the very basic and famous ones would be the valence and arousal, which is studied in the empirical examination by Russell and in his pretty famous circumlex model. But of course, along the way, researchers also argue that emotion is not just about valence arousal. There are other dimensions. So these dimensions seems to be never ending as well, because there could be always new dimensions that we look into emotions, such as dominance or power aspect of the emotion, whether we take control of the emotion or we are more passive with our emotions. The last group of the emotion-related concepts, which is also the focus of my presentation today, is on this notion of emotion intensity. And I would say that this is a relatively less explored dimension or concept of emotions. So intensity, as I think everyone would appreciate, that it's about not just about the frequency, category, or dimension of our emotions, but it's about the depth of our emotional experience. So just for example, that for almost hundreds of events that we encounter every day, we may just be slightly annoyed by a noisy neighbor, but we could feel extremely outraged by a terrorist attack. So similarly, we might be mildly worried about the examination results, but we can be terrified by quite a significant major disease outbreak, such as COVID. So emotion actually vary in a significant degree of its intensity over different categories. And this aspect has been discussed in big depths by psychologists Nico Frigida and Andrew Ottoni in their theoretical models, but relatively in the computational world is relatively less explored. Okay, so this is the focus of the notion that we talk about today. Whereas if I could move on to the next slide. There are two tools we applied for the COVID global sentiment study. So one tool is what we call Chrysophil. So Chrysophil take on the concept of emotion intensity. So essentially we look at the scoring model, which is a quantification model like Professor Sebastiani mentioned. in the very beginning. So this take on actually a quantitative view of emotion from the intensity perspective. So we focus on 5 analytic dimensions: fear, anger, sadness, joy, as well as the overall valence. This work also leverage some engineer focused work, including dashboards the team has built for tracking different social media platforms. So we have one platform that is focused on the Twitter data source, and the other one is focusing on the Facebook data source. Okay, just an overview. I'm happy to take on further discussions after this conference with anyone who is interested in the technology side. But I want to focus on the COVID-specific application studies and the learning points. So out of all this effort, basically we are responding to the ecosystem on 3 key questions. The first one is that, can we get a sense over a large scale of data? How are the public responding to the whole COVID-19, and what are the dimensions of concerns being covered? And lastly, the third one, which is still ongoing research with our team, is to look at, based on all the results that we can obtain from applying sentiment emotion analysis, how can we explain the differences and what implication we can recommend for the public agencies and the public health ecosystem to take on, so that they can handle this crisis in a better way. So the first important learning point is, as can be shown by this study, I think this is a study that we position as a rapid report that we share with the community, which Erik selected for this symposium. But essentially, you can see that by applying and looking at these 4 emotions, and then we take on the dominant emotion concept, and then we did a daily average of counting the frequency of the most dominant emotion. You can see that the timeline started from late January 2020, which is still on the very early stage of the COVID pandemic. At that time, it was still called nCoV. Until in February, it was renamed to be COVID. So one key observation that we observe is that at the very beginning, we have observed that the whole world is showing mostly fear, dominant emotions. So in a sense that this is quite reasonable, in a sense that at that time, this virus is still very new and there are a lot of uncertainties. So this was dominant by the emotion characterized by the anticipation of some undesirable events. But we have observed at the earlier time, for which we have surfaced through our science reports to the public agencies, that we do caution the monitoring of the anger trend, because by psychological knowledge, anger is a secondary emotion. So it is a combination of being very displeased about the current situation, as well as there is another element that we believe that other people are blameworthy for the undesirability that we encountered. So you can see that in the COVID data, we do observe that anger continuously increased at a global scale until there was a tipping point, which we can call it, that it overtook from fear as a dominant emotion at a worldwide scale. So this date is happened to be 12th of March 2020, which is the day after WHO made the announcement this COVID is a pandemic. And then if you recall that time, the then President Donald Trump finally announced COVID is a national emergency. And the second day after, the whole US stock market crashed. So those fellow researchers who study the finance domain might look at how this might correlate with the stock market. But from the global scale emotion trend point of view, we do see this trend continue to grow. And then it was actually still the peak of the emotion until today for most of the Western countries. You might also note that the joy and other positive emotion also have some kind of increasing trend. And then when we investigate the word clouds as a surrogate or proxy of the underlying reasons, we do see some gratitude and hope related to vaccine, for example, that can explain the increasing trend of the joy and positive emotions. So this is the first lesson learned. So we do see that emotion level sentiment trends are very sensitive to the development of significant events. This is at a word scale. So after this work, we continue to do a little bit more. We find that there are quite a lot of public health epidemiology researchers are interested in this kind of Twitter data, especially coupled with sentiment and emotion insights. So we have been continuously collecting the data, and then we are actually sharing this data set with the whole research community, for which you can take a look through the bottom link. Essentially, you can see that from 28th of January 2020 until today, so we have actually collected more than 150 million English tweets using these 4 keywords from Twitter's standard search API. And then you can see that, of course, the COVID keyword gives us most of the tweets. We have done a little bit more pre-processing to facilitate more downstream researchers to leverage this data set. So for example, we use LDA-based, we train basically LDA-based topic analyzer, and then basically this approach emerged several topic clusters, with the biggest topic cluster related to Donald Trump and worldwide news, different country mentions. So this could be a starting point to do more topic-specific sentiment analysis. On the other side, we also have received a lot of interest to see whether we can zoom in the global scale tweets data into geographical labels, because at least in the communication and public health research field, the geographic or location information is very important, especially in the context of COVID, where different countries are adopting different response measures. So it is of quite a lot of research interest in the public health and communication psychology field to look at how the different countries are responding. So the best proxy we can use, thanks to Twitter's open API, you can see that we were able to map the tweets, which is from the location attribute from the public tweets we collected. We can actually make each location name with country name using a GeoName database. So out of the entire data set we collected, we have close to 55% of the tweets can be somehow identified with a country tag. And this could allow for some investigation into the country-specific differences. So the last point is linking to what I mentioned just now. Because of the application of latest emotion analysis and geographical tagging, we started to notice there are quite a lot of significant differences. So this is the same Twitter data, same keywords. Of course, one key limitation is that we are mainly focusing on English language tweets. We do see that the same algorithm behind as well, but we do see that you can see that just pick these 4 countries for which we derive the data. We have seen that the emotion trend or trajectories are very different from country to country. You can see that from the USA and the UK, they are largely similar. Anger is dominating the emotion trends associated with COVID. And then our NTU collaborators could identify, for example, the most likely event that trigger the different kind of anger. Whereas you can see Singapore and India, which could be representative of Western but Asian but English speaking countries. We see that joy is dominating the emotions. The happiest moment, I think most of us live in Singapore, was detected on 14th of December last year, where Prime Minister announced the phase 3 reopening. and all the vaccination plans. So this apparently brought a lot of hope. But of course, some of the phase 3 opening didn't happen as events continue to evolve. So all the nightclubs, karaoke still cannot open. So you can see that this is very sensitive to the locality as well as geographic specific development. India has a very special trajectory, which actually still trouble the research team to analyze why, because we know that India is the #2 country that has the highest COVID cases. But instead of having a lot of anger and fear, we have seen a lot of joy. So we are still trying to investigate what could be the possible causes. Is it cultural differences or linguistic differences, or it is a situation that people are really very optimistic about the situation. So, okay, so I hope this gives you a flavor of what this piece of research is getting towards. As a summary, so you can see that at least there are two main observations we can gain from the COVID application case. The first one is that I would say that the emotion analytic tools from the public agency point of view, they are still relatively very nascent. But you can see that the trend is that public agencies and the health ecosystem started to appreciate the value of social media and sentiment analysis to help to ground their policy and population understanding with advanced technologies. And the second point is that it is important for our research to be able to accommodate not just sentiment analysis, as it's a big sweet case, right? And like Erik mentioned, that we need to overlay sentiment emotions with other important attributes such as geography data, as well as a different aspect of the topics, because the real world problem statements usually come very comprehensive. They will ask a lot of questions where a particular technology might not address, but it is a combination of multiple technologies. So as future work, we are working on 3 directions right now. So the first one is that we are looking at, not just looking at the Twitter data, but we are trying to overlay and correlate other more so-called objective data, such as the announcement from health authorities, such as MOH and WHO. We also are interested in how media played a role in shaping the different emotions from the population, and even to look at how the different COVID virus genomes could correlate with the Twitter sentiment and emotions. The second direction will pertain to, we want to leverage more theoretical lens to help us interpret why there are such differences observed in this global scale COVID emotion differences. And lastly, that we are hoping to get a little bit further in working with the communication scientists to look at the so what question. So that, for example, how to recommend strategies when people in strong fear versus strong anger, and how they can nuance their messaging to be in a more sensitive manner with what the public is having their concerns. So with this, I want to thank everyone, and I'm happy to take questions.
Thank you, Yinping. Any questions?
Can I have a question, please?
Sure, please.
So thank you, ma'am, for your presentation. Somewhere you have mentioned that the which is two events are very much related to the sentiment analysis. So do you relate events? For example, in one slide you mentioned that Trump is seen being discharged from hospital. So this event was occurred, and over there the anger sentiment was dominating other sentiment. So how you relate that this discharging Trump from hospital caused the anger sentiment dominating other sentiments in the overall tweet data?
Okay, yeah, sure, I understand what you mean. So here, what I show here is a relatively simplistic illustrative graph to highlight the point of the sensitivity of emotion analysis. So in our more confirmatory analysis, we actually dig into the tweets of the particular day, and then with our algorithm that actually sample different emotion over anger, fear, sadness, and joy. So the first level we track is to using a typical word frequency analysis. So when we look at the anger, so all the subset of the tweets over that 2 days, right? That is classified as anger, for example. Then we'll look at the unigram and bigrams to look at that, to give us an initial sense, what are the dominating words. So this gives us a starting point to attribute the most likely event that trigger anger. And then our communication scientist collaborator will also look into will screen through the entire sample to assure that this is the most likely events that has been associated with this particular emotion peak. So this is like more like a two-step approach by using word cloud to get the initial sense to form the hypothesis. And then there's a confirmatory step by the communication social scientists to confirm this is the case. So far, we don't have an automatic way to assert this must be these particular events because emotion can be very complex. So we don't have an automatic way yet. I hope this addresses your question.
Oh, thank you. Thank you very much.
I think for future work, it would be interesting to apply those techniques that we use for aspect-based sentiment analysis in this context to do some sort of aspect-based emotion analysis so that you could know which emotion is related to which topic.
Yes, that could be quite interesting. So because of the research focus, my team doesn't really continue to dig very much into aspects. We focus on the depths of the intensity and the experience, and also the population level of well-being. But it could be very fruitful to look into that because we share this data set actually. It's downloadable from the link if you follow this archive paper.
Is it or
it is already available.
I mean, there are labels with the tweets or not?
Yes. So in compliance with Twitter's TNCs, right? So we share the tweet ID, the user ID, but not the tweets. But we also share all the detected topic labels and sentiment, emotion, intensity labels.
Oh, great.
For the data set. So you can hydrate the actual tweets using the free Twitter API.
Cool. Okay. Thanks again, Yinping.
Thank you, everyone. Thank you, Erik.
Hi, everyone.
Hi.
Can you hear me?
Yes.
Hi. Okay. So I will share my screen. Okay. So good afternoon, everyone, and thank you, Erik, for inviting me. And it's my pleasure to be here to give a short speech on the conversational sentiment analysis. So conversational sentiment analysis has attracted increasing attention in the past few years due to its promising potentials and application values. So for example, conversational sentiment analysis is an important topic for developing empathetic chatbot. So let's take a look at this example. Here, the speaker said, I finally got promoted today at work. So the speaker felt proud since he got promoted. In a previous dialogue system, the response of the conversational agent is, why would anyone promote you? But this seems inappropriate in this situation. So if we incorporate the emotion prompt into the dialogue system, we can generate an empathetic response that is congruous. That's great. So in this case, the empathetic chatbot achieves better human-robot interaction. So here the pre-trained emotion classifier is of vital importance. So now the question is how to get such a pre-trained emotion classifier. So before that, we need to give a clear definition of the conversational sentiment analysis task. That is, the target of this task is to detect the sentiment or emotion of each utterance in a conversation. The emotion can be happy, sad, frustrated, or some others. And obviously, the context information is the main difference between the conversational sentiment analysis and single sentence sentiment analysis. The context information sometimes enhances, weakens, or reverses the raw sentiment of an utterance. Here is an example. In this utterance, I had planned a hike this week. So it is hard for us to determine the emotion of this utterance. It can be happy or neutral. But if we look through the previous utterances, we can find that the male speaker have a math test in the next week, and he will not have enough time to prepare for this math test if he still carry out the plan of hiking. So in this case, we see that the emotion of this utterance is frustrated. So in addition to the context information, the speaker information also serves an important role in this task. So now we are clear about this task. So the problem is how to classify the emotion of each utterance considering its context information. And my solution is that if we can incorporate the context information into the embedding of the current utterance, then this problem becomes a normal sentiment analysis task. And in this case, we can use a high-quality classifier to classify the context-aware utterances. And the tools used in this solution are the neural tensor networks and two-channel feature extractor. And I will briefly explain these two parts. So this is the neural tensor networks. So supposing these are the concatenation of the embeddings of the context and the current utterance. And then we can use the neural tensor slice to capture a specific type of relationship between them. And if we apply k different neural tensor slices, then we can get a k-dimensional embedding. And here we assume that this embedding is the embedding of the current utterance with the context information incorporated. So this is the neural tensor network. And for this two-channel feature extractor, the motivation is that the previous study demonstrated that this two-channel structure has better performance compared with the single-channel structure. So now, with these tools, we further design a new model for the conversational sentiment analysis task. So the model has two variants. And here we can denote ERU as a combination of the neural tensor network and the two-channel feature extractor. And then if the ERU are combining in a recursive manner, then this is the global context version. And in this variant, each utterance in the conversation has global context information incorporated. And if we only use the adjacent utterances, then this is the local context variant. And in this variant, only the adjacent utterances are regarded as the context of the current utterance. So this is the model. And next is the experiment part. I will skip this part. This is the result. The result demonstrates that the proposed model gets better performance compared with the baseline models. And the interesting thing is that local context version gets slightly better performance than the global context version. And one possible reason is that the global context may contain redundant information. So in the previous slides, I gave a solution for this task. And then let's come back to the research of this conversational sentiment analysis task. So first, I want to talk about the resources. So in addition to the MELD, IEMO-CAP, and AVEC dataset, we also have the daily dialogue, Emory NLP, and EC dataset. And also we have the scenario essay. This is a new dataset. It covers a wide range of topics, including the shopping, college life, politics, work, and food. The interesting is that this dataset also contains the interaction patterns between speakers, question and answer, offering and response, greeting and greeting. This is very interesting. But even though we have a lot of datasets, this dataset has the drawbacks. For example, the IEMO-CAP dataset, if you read the conversation in this dataset, you will find that the quality of the conversation is not good. And the conversations, they are quite similar to each other. So this is not very good. And AVC is a small scale dataset for MELD dataset. So the average number of turns is 10, but there are more than 5 speakers in most cases. And also the sentiment expressions rarely exist in these MELD utterances. So even for our human beings, it is hard for us to understand the conversation without background information. So for the data dialogue, it does not provide the speaker information. And Emory NLP, it is a TV show script collected from the friends. So it is a little bit different from the natural conversation. And EC is not a commonly used dataset. So in this case, we conclude that we still need a high quality dataset for this task. And then based on my understanding, I try to list some research challenges. So the first one is that all the aforementioned datasets are all English datasets. So maybe in the future, we still need more data sets in different languages. And the second one is that except for the emotion and speaker information, we also have additional information like the aforementioned interaction patterns. So how to make use of this additional information is still a challenge. And the last one is that this task is conducted at utterance level. And we all know that an utterance may contain several sentences. So the utterance may be very complex and contain complex sentiments or sentence shifting. So this is a challenge. This is challenging for both the dataset construction and modeling. And here, based on the most recent research, I list some possible research trends. So the first one is the multitask learning. You can use design some auxiliary task to improve the performance of the main task. And also we can treat this conversational statement analysis task as a sequence tagging task. And then we can use some algorithms used for the sequence tagging task to do it. And also use the external knowledge, like common sense knowledge is also very important, but it's also very important. So find a better way to incorporate this common sense knowledge is still a challenge. And the last one is to considering the implicit conversation structure information. So as mentioned before, through the conversation analysis, we already know some interaction patterns. So in the future research, we can try to incorporate these interaction patterns into the conversational statement analysis task. Okay, so that's all. Thank you.
Thank you. Thanks for the presentation, also for the insights and the future trends. That was very interesting. Any questions from the audience? So one of the issues that we discussed in other presentations and that you discussed as well is like the integration of external knowledge such as domain knowledge or common sense knowledge. But since we are moving towards algorithms that are more and more sub-symbolic, how do you think these can be merged with knowledge that inherently, at least initially, is symbolic?
Actually, I didn't think a lot about this, how to incorporate this common sense knowledge into the conversational statement analysis task. But I think one possible way is that we can also combine this common sense knowledge with the knowledge in the conversational structure, and try to build a more powerful model in this case.
Right. Yeah. I mean, I didn't expect you to have the solution for this. Whoever solves this solves like the holy grail of AI. But yeah, this can be an occasion for all of us to discuss and brainstorm.
Yeah.
Thanks again for your talk.
You.
Navo, are you here?
Yeah, hi, Erik.
Hi, Navo.
Yeah. So, shall I share my screen or?
Yes, but I need to make you co-host first. Find you. Okay. You should be able to share your screen now.
Right. Okay, I need to restart this Zoom. Sure.
Okay.
Yeah, all right. I'm coming back.
That's what happens when you do it for the first time. You need to grant access to Zoom. A lot of technical problems, but again, this is the first time we go virtual, so maybe next time we'll be more well prepared. Again, I'm sorry that we're running out of time already. We're so beyond our schedule, but this is the last talk, and then I will briefly conclude the symposium. if all the speakers agree, I will make available either the slides or even this video for everybody who registered to watch it again, like many of you have asked in the chat. So I see that Navo is back.
Yeah. Will you make me a course again? Yeah.
Okay, you have the power.
Yes.
Yes, we can see.
Yeah, great.
Can you make it full screen? Okay, perfect.
Yes. Yeah. Thanks, Eric, for the invitation and everyone for joining us today. So this is the work we did last year, a small work on empathetic response generation. We know it's useful in many empathy. I mean, the concept of empathy is useful in medical domain and customer service. So it has wide spread application in the industry. So to this end, we proposed a model for this task. So first, let's define the task. So as input, we are given this excerpt of a conversation where we have to respond to the last utterance in the excerpt, and we are also given the user emotion as input. And yeah, so this is the empathetic response that the model needs to generate. So the basic idea behind it was that empathetic responses often mimic the emotion of the speaker at varying degrees. So we will study this with few cases here. And so this is a case where the user emotion is positive. So for example, here my son graduated. So the response is, that is great. How old is he? So it's a natural progression of the conversation, and which maintains the positive emotion. And on the other hand, for negative user emotion, we have here, so we observe a mixture of both positive and negative emotions. So the positive emotion usually indicates some silver lining from the responder. And from these examples, we can use these takeaways. So what we observe is the grouping of the emotions, that is positive and negative. Negative is important for empathetic responses. And we are often observed that the emotion of the user is mimicked by the responses. And also important is the mixture of emotions, which is positive and negative groups of emotions. So how do we model this? So first, the task at hand is to make the emotion group. So we divide the list of emotions that are of 32 strong, and we group them into two groups. Some of the emotions like anticipating, excited, and surprised are ambiguous. It could be either positive or negative, depending on the context. So this is the overall structure of the model. So first, we do the standard thing. We take the context and pass it through transformer encoder for input encoding. Next, to infuse some emotional understanding into the model, we classify the emotion of the input context. To achieve that, we represent the individual emotions with their individual emotional embeddings, and we compare with the emotion input and encoding to get the emotion class. Moving forward, we use the emotion representation of, input representation to generate the distribution of the different emotion groups. So probably we generate a probability distribution here for each of the emotion groups. So you see mimic and non-mimic groups. So mimic group represents if the emotion is positive, the input emotion is positive, then mimic group is the positive emotion group. Otherwise, is the non-mimic one. And we use this probability distribution to get the response emotion representation. And with the response emotion representation, we get the response emotion specific input representation. And for each positive and mimic and non-mimic group is fused into a single representation, and this fed to a transformer decoder to get the final representation. So we evaluate this model on this data set called empathetic dialogues, which consists of 25 dyadic conversations from open domain, and all the 32 emotions are roughly uniformly distributed. So we compare our model against these two baselines, which is the first one, the multi-tier is basically a transformer encoder decoder setup. And the model is a state-of-the-art model which shares the same decoder with us, but the encoder with us, but their decoder has emotion-specific sub-decoders whose outputs are aggregated and fed to another decoder to get the final response. So to evaluate the response, we basically rely on these three human evaluated ratings. So first one is empathy, that correlates well to emotional understanding of the generated response. Then we have relevance, which basically evaluates the topical relevance to the input context, and fluency indicates the linguistic clarity or grammatical clarity of the sentence. So we see that in our experiments that our model beat the state of the art, the baselines when it comes to empathy and relevance. However, it struggles a bit for fluency. The most possible cause is that the very architecture of the model promotes the empathy and relevance over fluency. Another important thing to notice is we have fewer parameters than the state of the art, yet we achieve overall better result. So in this experiment, we pitted the responses from our model against the other baseline models, and we asked the annotators to state which one do they prefer. So most of the time they prefer our responses generated by our model. Yeah, so here we perform some ablation tasks. So the main two takeaways from our model was emotion mimicry and emotion grouping. So we take those different concepts away from the model one by one, and we check its response. I mean, how the model responds to it. So we see when we take away the emotion mimicry part, the empathy drops a bit, but the relevance increases. So, but also the fluency decreases. And we again, when we take away the emotion grouping and emotion mimicry as well, we see the worst performance here. So possible reason behind the drop of relevance for the removal of emotion mimicry is possibly confounding effect that courses the same set of parameters to learn both positive and negative emotions. So another study we did with we see how the emotion understanding is affected by the removal of emotion mimicry. So on the right side, you see when the emotion mimicry is implemented, the emotion grouping of different emotion levels is much better with respect to its positivity or negativity. But on the other hand, on the left side, you see is this interspersed across the space, and they are mixed. So there is no clear cluster there. So here we show some case studies. So on the left one, you see the response generated by our model uses contextual information from the input, which is considered, I mean, obviously considered a better response and more natural one as opposed to the one from the state of the art. On the right, you see that the MIME is able to, I mean, our model is able to interpret the events described in the context as a beautiful memory. but our model also falters when it comes to fluency. So you see the response, while it's empathetic and relevant, the quality of the grammatical structure is a bit off here. So in conclusions, our main contributions are introduction of emotion grouping, mimicry, and the stochastic emotion mixture, as opposed to the static one from the state-of-the-art method. In the future, we would like to re-level the ambiguous levels. I mean, we would want to split them into two positive and negative polarities of the same level, and we'd like to do some improvement to make it more fluent in terms of grammatical quality. Yeah, thank you. Any questions?
Thanks, Navo. Any questions? So how did you build those emotion embeddings? Where do they come from?
Yeah, so initially those were, I mean, randomly initiated, and during the training process, it's just fine-tuned.
Right. So as you mentioned in the beginning, actually there are some so-called emotions that for some people are not even emotions, like surprise, that are very contextual. So if in your future work you say that you want to put this surprise somewhere, actually,
you're probably positively surprised or negatively surprised, something like that. Yeah.
Yeah, I mean, just an advice for future work.
Yeah, sure.
Okay, thanks, Navo.
No, thank you.
So we're nearing the end of the symposium. I'll just very quickly give you an elevator pitch of what CentiGnet 6 is. I hope you can see my slides. So CentiGnet is something that we've been developing for the last 10 years, and we arrived at version 6, which comprises of 200,000 concepts. What's new about this version is that we're making heavy use of deep learning to actually build the symbolic representation. So for example, these dotted links that you see here in the graph are actually built by means of deep learning. So you can download, you can use this knowledge base for free as an API, or you can download it in different formats, including XML. And we also have embeddings for each of those 200,000 concepts that you can also download and easily integrate in your deep learning algorithms. We share a lot of our code on our GitHub. For example, the code that we called context-to-vec to be able to for example, in this example, you see that we've tried to find all the possible ways in English where you can express the concept of buying something. And this we do in order to create this representation that I shown you earlier, create some sort of primitive by using lexical substitution to find all the possible ways that we can express a specific concept, a specific meaning and sentiment in English. And so what's new in this latest version is that once we do that, once we find all the possible ways we can generalize a specific concept using deep learning, then we also try to give it some sort of symbolic representation, like in the bottom left corner, you see how buy is defined as a special case of barter. And barter, it's explained in terms of two primitives, get and give, which are in turn defined in terms of the super primitive have. So this is a way we are attempting to reduce the symbol grounding problem. And CentiGnet 6 is also based on this new emotion categorization tool model that try to solve the problems that, for example, Yinping has talked about, where many other models were only looking at categorical or dimensional or intensity categorization. Here we're doing all of these things together at once. So I don't want to bore you with the details, but you can find information about this. This is the revisited version. The original model was proposed in 2012. The revisited version has been proposed last year. So you have here 4 different affective dimensions, and both, all of them have the positive and negative part. And there is also a formula that can connect emotions with polarity, which is also a problem that many of you have experienced and discussed about. And then, of course, also some guidelines on how these emotions can be combined to create more complex emotions, including the usage of expectation and surprise, which in our model are not are apolar emotions. They are not really affecting the polarity. They only acquire a polarity once they are coupled with another emotion. So this can be something that, for example, can be useful for Navo. So that's it. We use CentiGnet and the hourglass model for many different applications. You can look at these on our website. Some of these have been touched by some of the speakers, like Frank talk about financial sentiment analysis, Hwee talk about conversational sentiment analysis. And last but not least, a little announcement, there is a new, if you use CentiGnet, the hourglass or any of our tools, you're welcome to submit your work to this new section of cognitive computation, which is specifically on sentient computing, which is this approach that we're taking to sentiment analysis, where we try to use a hybrid approach of AI, where we use both symbolic and sub-symbolic AI. So this concludes the symposium. Someone has written something on the chat. It's just a direct message. Okay, so again, thanks for participating. I will, if the speakers agree, I will share these slides or the video on, I will send you an email about the video or the slides. And thank you very much again. You can follow us on different channels on Facebook, LinkedIn, to find about also new call for papers that are specific to this exciting topic of sentiment analysis. And the next S3A will be in 2 years' time. So looking forward to that, and have a good evening and talk to you soon. Bye, everybody. Thanks to all the
Bye-bye. Thank you to all.
Thank you.
Bye.
Thank you.